Hey, hi everyone. Happy Sunday. It's almost the end of January, first month of the year. Can you believe it? I can't quite. Got our chat up. I set up my continuity camera to do its continuity camera thing. So we should get a better look at the screen today. Check it out. Wait, there it is. How's that? And I'll just mute mute myself here. Hold on a second whilst I also set up the headphones. I think I've set up to monitor my microphone earlier. Yeah, there we go. Much better. Fabulous. There we are. We got all the views. Hey, hi. 5 different views just for you. All right, we got the cam set up. We've got code in a pile. I've been working on some input shaping stuff, which I'm going to show you in a minute. Here we go. Mute. We can mute that. I don't know what else I'll be doing with this. Oh, I might put up the Discord. That might help. But mainly we're monitoring chat today. Let's see how the desk and code scene looks. Oh, the chat seems. I did set up the chat. Hold on a second while I get that link. I think it's. There we go. Oop. Hello, chat. There we are. Live chat. As usual, I don't expect a lot of you today. Kind of a impromptu announcement, but you know, Saturdays are just overloaded with people doing streams on 3D printing. I don't want to be competing with Nero and everybody else, and you know, 3DPN and all that stuff. So I'm trying to find a little corner of Sunday that I can utilize. So today, being Sunday, seems to be a perfect day for it. So what are we working on? Well, let's take a quick look at the pile. I just fixed up some stuff to make the y-axis possible to just have an x-axis and an e-axis and no y for most situations. I'll still have to continue that work because, you know, who knows when you'll want to have a single you know, motor driving something. I'm thinking of things like, you know, something obscure like a camera track, or I don't know what you'd use a single axis for plus an extruder, but you never know. There might be some use for that kind of thing. Anyway, it just makes the code more what's what I'm looking, consistent, I guess, if I do this kind of thing. So as you can see, it's like has y-axis, it's just getting thrown in more places. And then I had to make a little thing called has x-axis that's always true. And then tweaking the types, which is, you know, low level, but not that low level. I was also thinking of getting rid of these no-ops in types, which is why I'm here. So let's just take care of that real quick. A no-op is just a void 0. It casts the number 0 to void and does nothing else, which basically the compiler throws away. So what I really wanted to do was get rid of these, all these noops, no ops, and just let them be semicolons. Because they're just, you know, really just dummy things anyway. So how many commas do we have anyway? Too many. All right. And it was kind of also just to make these things line up, which is not that important, honestly. Anyone else? Okay, that takes care of all of them. So that'll make it slightly neater and, as it were, neat-ish, we'll say. And I'll just amend, because why not? So that's going in ahead of the changes that apply to input shaping, which is a new input shaping. This is exciting. Now, as you may know, some of the reviewers and our favorite 3D printing mavens on YouTube, Chris Riley and 3D Jake and some others, have been starting to cover Marlin's ZV input shaping by Tom Brazier. And it's getting good results, which is, you always worry about something new. But we did mark it experimental, and part of that is because the G code may change a little bit. I've been thinking about the way it works now is you set, like, you have an F parameter, which is your frequency, and then you say X, Y to set X and Y, or just X or just Y to set it for X or for Y. And I'm thinking, well, maybe it would be better if we had like F as a flag. Hey, we're setting frequency, and then you set X frequency and Y frequency. But the way it works now is kind of like cool because you can set both at the same time without having to say X frequency, Y frequency, and then F as a flag. So it's a toss up. You never know what you're going to do with these things. So anyway, as I filter through this kind of stuff, I don't know why exactly I have the Ender 5 up, because I don't know I'm going to get to any Ender 5 stuff today, but I did want to get the continuity camera up and have it be, possible to point it at the printer and then also get a close-up of the screen at the same time. So that was kind of what I set up today, and we'll use that whenever I get back to the Ender 5. It may be today, it may be tomorrow, it may be next week, we'll see. But at the moment, I just wanted to kind of like give you guys a little bit of a sneak peek at the Ulendo code and what it entails and what it means for input shaping going forward, and what I've been doing with it, just as a general, give you that insight into kind of cleanup that we generally do every time we get a contribution, or at least when we get fancy contributions. This particular one is going to introduce a new thing called fixed time motion control, which is the basis for then adding on the input shaping. But some of that input shaping stuff is also related to, some of the fixed motion stuff has to redo the linear advance a little bit. It re-implements linear advance, and it re-implements, I don't know if it touches S-curve. I think we may be not able to use S-curve with it, but it basically is replacing the motion system to some extent. And so anything that we want to include, like mixing extruders and things like that, we'll probably have to either re-implement, or, as I'm kind of thinking, as I get more familiar with this code, I may be able to incorporate it at a similar level where the current input shaper is at, and see if that helps. It may be tricky to do, so we'll see. Meanwhile, all this compile with no y-axis stuff, we'll see how that works out. I was just cleaning that up, and this will probably end up getting rebased on that. So the initial stuff that we got from Ulendo is pretty neat. I'll just go to the initial revision. As you can see, it adds a thing called FXDI control, which stands for fixed time control. And this has all been cleaned up a little bit, so what I'm showing you now is the sort of pre-cleaned up version of that stuff. But in essence, we have like a default mode, and I'll come up with a better way of defining these so you don't have to have fancy camel case things that you have to type in or copy from somewhere. It's a bit of a hassle. I will instead, I'll use just, maybe this part of it, the end part, and then it'll get a fixed or a prefixed or a postfixed onto this when we use it. So in the meantime, these are like the default modes. We'll include just plain enabled. One of the options will be to have multiple input shaping options available that you can switch between. So even at runtime, although I think to optimize this, I'm going to make it so you can turn off the ones you're never going to use and just keep the ones you are going to use. That way it's less code and less RAM and probably less overhead. because it is looking at, which one, each time it's going through, it's like looking, am I using input shaper 3 or 4 or 10 or what? And it's picking the algorithm to use and variables and stuff at that time. So anything I can do to sort of optimize that and pre-calculate and all that kind of thing ahead of time will be useful. So it also adds advanced ops. So this is the master toggle right here. And currently for this version of the branch, oh, by the way, based on 211. So this is ahead of, or you could say it's, we have 212, which has our input shaper by Tom, ZV. And then we have this built on 211, so it kind of exists separately. So it's a completely separate thing, and what I'm doing is trying to bring the two together, not necessarily merge them, but just make it so you can compile one or the other and get one or the other without having any major impact, and they don't interfere with each other. And they're, in general, the code that they use is not dissimilar. It's very dissimilar. So it's not the same. It's unique. So then we have advanced options, and that includes things like your time step. You have this 1 over thing here, which I think if that's always going to be 1 over, then we can eliminate it. But I think it's suggested that it could be. We'll have to figure that out, whether it's always consistently that or not. I need to continue to ask these guys at Ulendo for a little help, because it's, tricky stuff. It's definitely past my pay rate. Way over my pay grade to do this kind of thing. So we have things like here, stepper timer rate divided by this, and so, if that's always going to involve the timer rate, then I'm going to basically remove that and replace it. So there's changes that are coming to this. This is all very much set up to be low level. This is kind of the low level, as you can see. It's advanced configurations at this level. So, the main options you'll use will basically be your default frequencies, similar to what we have now. And then you have a default K for linear advance, which we're going to be, since we may just share the linear advance values between the two, between regular linear advance and their implementation of linear advance. And then there's zeta, and I believe we have something like that we set directly now ourselves. And then there's a thing called vibration tolerance for EI input shapers. I'm not too familiar with EI as an input shaper, but we can look at that and what the theory is on EI input shapers. The name of an EI input shaper is interesting in itself. It's called, what is it? EI. There are better labels around here somewhere. We'll get into those. I'll probably want to make a long comment on all this. I've done some cleanup, but I haven't added longer comments because I'm still just trying to wrap my head around it as I'm cleaning it up. So one of the things you'll see is that in the Marlin core, inside of our main loop, this was actually at idle done. It'll probably be before idle done, because this is everything before idle done can happen after Marlin is initialized, but before idle done stuff, the Marlin has to be initialized. Stuff after this will happen even if it's not. So right now we have idle depth, which this is just a thing to count how many times idle has been called from, like in a, what am I saying, recursively. If idle calls something and then that thing ends up calling idle, it goes up, it increases this idle depth. And then we can use that to debug and figure out, oh, there's a stupid bug that it continuously comes back to idle. There are times when you do want to do that, but there's usually, you don't want to go more than 2 levels or 3 because your stack will blow up. That's why that's there. But anyway, one thing that's happening is that it's calling a thing called loop whenever it needs to, which is basically monitoring the status of your motion and in the user thread, which is interesting, and then handling that. I'm thinking for multi-core or at least dual-core boards, which will be coming more and more, arriving more and more, I should say. There'll be 2 cores or more, so we can use loop 2 or to actually have a second core execute code, and then we just have to, do mutexes and weird stuff if there's any shared variables between the two. We'll still be running the single interrupt for stepping and so forth, but this could run on another core, which would be neat. And then we could move some other things to the other core as well to optimize those things. And if there's multiple cores, who knows? We could use one for doing the LCD and so on. I have heard, so I'm paying attention, that our current input shaping actually does cause certain displays to throttle, or they're less responsive, as it were. The reason for throttling is when this planner seems like it's going to starve, like it's not, say, half full or more, it starts to slow down the display updates, because that planner needs, it's being fed by the user thread, by the main thread, and the main thread is also handling the display. So it's like, if we go off to draw the display, or at least even one just small stripe of the display, and it takes a while, then we're not feeding the planner. So I think there's probably a little over-aggressive in the throttling, so we may be able to tune that. And I'll have to look at it and see where that's happening and what we can do about it. Meanwhile, there's also a new code. This is not going to be in the final version. The new code will still be M593. We'll just change the parameters, I think, for this particular mode. Right now we're using M593 with maybe, it doesn't have that many parameters. This adds a couple. Also, like, it's not going to be M950 plus an M parameter. Although, that's Marlin can handle that, but we kind of want to keep the protocol from getting too weird. So one of the things we've sort of disallowed is using M as a parameter, G as a parameter, and there's one other. Sometimes we use T, but we're careful with it. But G is particularly G because in traditional Linux CNC style G code, you can chain commands. Like you could have G80 blah, right on the same line, and then G81 right on the same line. Or you could have something like, I think there's when you're in different motion modes or time modes, feed rate modes, you will be like in a feed rate mode, but you can use this G in the front of your command to say, oh, for this one command, just do regular feed rate mode or whatever. So it's one of those things that we want to preserve. So that's one of the reasons that I've disallowed G as a parameter in codes that start with G, and tried to really avoid using them in codes that start with M as well. So you'll see if you do find codes that use G, it's an oopsie. But in the future, it may matter. It may never matter. But it's one of those things I just kind of like held on to for the sake of maybe compatibility issues in the future. So we have M950, and as you can see, it's a bunch of stuff. You'll be setting a particular mode. It'll do some update stuff. As you can see, oh, here we go. We've got ZV shaping, ZVD shaping, EI shaping, which we'll be looking up more about. And it uses, it calls this update shaping A with these two values. I think I'm going to make those default values, default parameters, so you can just call it with nothing, and it'll basically reset it to these values that are set in the config. And then you got hump EI shaping, or 2-hump EI shaping, I should say, 3-hump EI shaping, and MZV shaping. So all of these are slightly different, and we'll look at the code that each one entails in a second. I've been peeking at the RepRap firmware code a little bit. That doesn't implement all of these right now. There's a couple missing, or at least last time I looked anyway. But it has a good overview of sort of what it's doing. The thing about RepRap firmware is it's a lot of indirection. Like, the underlying system for motion is actually more of a, it's almost like this separate time slicing unit called dynamic motion system or something. I can never remember the name, but it's really cool because it's very amenable to, just assign this thing to it, this pin, and it'll step it, whether it's a stepper pin or not. It'll just do whatever, and you can kind of like use it to drive any new devices that come along that use stepping or whatever, or that need regular pulses, or so it's kind of a really cool thing. And of course, their way of building input shaping into it is very different from the way that Marlin would do it with its current motion system, and it's probably closer to the way that Ulendo has done it here. So we may compare Marlin's input shaping to Ulendo's input shaping a little bit here, but definitely more in depth in the future as we get more understanding of how this all works. It's definitely, again, it's beyond my pay grade. I'm no PhD, and I know my limits. I can hold about 2 things in my head at once, and that's about it. And sometimes they get reversed, so keep a pen close by and take notes. So here we have, some of the things I've optimized here are clearly going to be the messages. These are using regular C strings, and we need to use program strings and so on. So that's already been done to a large extent. But as you can see, there's like a dynamic frequency mode parameter, so you can do that. And there's one that's based on the Z position, which is really cool. And that was actually one of the requests that came up. Was as you move, your model gets taller, or the gantry is higher up, and so the swing of the machine is going to be more pronounced, but it may even achieve different frequencies at different heights. And so the machine itself is actually changing dynamically, and therefore having something that's based on the Z position makes a certain amount of sense. But it means you'll have to do extra tuning to figure out at different Z positions what kind of resonances you get, and then work on tuning that. And there may be some automatic tuning that we can do, although we don't have an accelerometer. One of the suggestions, which I heard, which we were discussing recently, which was exciting to me, and I posted it immediately on Bostodon, was that people are using their phone accelerometers and just taping the phone to the bed and measuring the resonances in 2 dimensions that way, and even 3. You can measure 3 different accelerations. So conceivably, you could measure all the resonances with your phone just by sitting it on somewhere on the frame. But you kind of want to measure the resonances on the bed as you're doing bed motion. You want to measure resonances on the x-axis as you're doing the x motion, and you could even measure resonances at the bed with your phone as you're doing X motion. And we could run some of the same kind of weird motions that like your Carbon X1 and your Clipper firmware do with accelerometers to measure the different responses that you get at different accelerations and frequencies. And that would be interesting. We'd have to find some way to pair the phone with Marlin, but in general, I would think the best way to do that kind of thing would be, make a little app for the phone, maybe write some up in Python that we can compile, that you can run on your Android or your iPhone, and it'll measure the resonances and then give you G-code to send to Marlin and try out. So that would be kind of neat if someone wants to go for it and try that. You know how to write an iPhone app or an Android app, then go for it. I'm sure there are frameworks that allow you to write a Python script and then turn it into an app that runs on a phone. How complex and fancy you can get with that, reading the actual hardware on the phone, will depend on the framework, but I'm assuming that the accelerometer is something you can easily access through these frameworks. I haven't looked yet, but I will explore it pretty soon. A lot of my focus right now is going to be on wrapping my head around this, getting the motion code really tuned in as much as possible, and then looking at other improvements that are kind of really in order right now. One of the things I've seen, not to go too far afield, but Prusa firmware has recently had updates to do things like with their thermal runaway, instead of just going to kill mode, it gives you a chance to recover. That's something that you definitely want. It also has added some dynamic observation of the temperature and a little bit of modeling, and that's been really good. So it's similar to our MPC temp feature. But in addition to that, the thermal runaway or the thermal monitoring is much smarter. It's actually watching the heat dissipation and stuff like that. So how much heat are you losing over time? How much energy is required to bring it back? And it'll notice if, for example, it takes less energy to heat it up to the new temperature because it's not losing heat as quickly. And it'll assume after a certain point that there must be a blob on the nozzle that's causing it to not cool down quickly enough, and it can actually catch one of those print failures where a blob is starting to build up on your nozzle. And if the blob is, you've seen how those can get, like, you can get your whole extruder can get covered in melted filament when it goes really bad. So the sooner you catch that, the better. And it apparently can catch it pretty early. So even if the blob isn't too big, it'll like catch it, and then before the point that it's actually gotten up into your extruder and started to explode all your parts and ruin everything. Of course, the main thing with that is you want to make sure your filament continues to move. Sometimes those clogs, those jams can get caught by just observing the filament motion. So the more smarts and the more sensors you have, of course, the safer you can be. But that's something that I would love to get into Marlin, and we can all benefit from that, I'm sure. It's a little more intensive, computing going on there, but not much. I can't imagine it's much. You're just kind of looking for certain conditions every so often, that you can monitor every couple seconds and say, oh, yeah, the temperature only went up by this much, or it stayed warm and it shouldn't have, or whatever. We could also start adding things, which I think would be cool to add, like in the first time setup. Another thing on our mind for the coming year, first time setup wizard should do things like, considering that Marlin can run like on all kinds of hardware, and you can make mistakes when you're setting up your hardware by setting the wrong pins, and all kinds of funny things can happen. Your settings could be corrupted from a bad EEPROM, or who knows. Like having something that can, it's at first startup, do those tests to like check to make sure your hot end is cool, to do the PWM tuning or the MPC tuning as part of the setup, and give you feedback on your end stops and tell you that they're all working all right, and just, really just give you a confirmation that everything's working well. Those kinds of things would be nice to have. Of course, each of those things requires more RAM, and so they're the kind of things we can definitely do on the bigger 32-bit boards, and even some of the smaller ones, because they're all bigger than your AVRs generally. So we can definitely fit more functionality. Like if you're only using 80% of your flash, then we should be filling that up with more useful stuff and more features for you, that hopefully don't get in the way and slow things down. Anyhow. Yeah, so as you look at M950 here, you can see that there are some interesting things going on. We've got flags based on, which modes you're in. Does it use a frequency? Is our frequency good? And things like that. We're also, considering X and A. This is one of the things which I'll also quiz these guys on, is, how well is this adaptable to Core XY, Delta, SCARA, all the, even polar, where you have a hanging chain holding a pen. You can imagine certain types of input shaping would be really useful for that, to keep the thing from like shaking around and wobbling all the time. So anything we can do to like, tune these ideally for your particular printer or particular type of machine, whatever it may be, CNC, pick and place, doesn't matter. It all applies. Whatever we can do to like make that smoother and better, totally going to be most welcome. So as we move on to G-code, of course, the M950 is being added. Again, this is totally not the final version. M950 is used by RepRap firmware for some other thing. I forget what, but it's definitely like not related to input shaping, and I want to make sure that we use codes that are distinctive. So we'll be doing that. So that's your G-code, and M950 will be replacing that. I'll look at fixed time control in a second. Meanwhile, in the planner, the only difference here is that it's checking to see if it's busy based on, is the fixed time control busy. I'm going to be changing the name of this to, I think I'm going to call it either FT motion or probably FT motion, I think, because it's just, it makes sense. It should have motion in the name. And then in the future, if we have other types of motion, they'll be like, you know, JK motion or Yo Mama's motion, or whatever it happens to be. Meanwhile, yeah, this flag is just hanging out, FXDI control busy. I notice it's static here. So what's up with that? Because it's not being set. Well, that's actually not a big deal. Although declaring it here is strange. Oh, I see. It's inside the class. Never mind. It makes perfect sense. So yeah, and here it is, busy. So it's a busy flag on the planner for the fixed time control. And as you can see, it's been doing some things like am I on, basically. If I am, then use 0 for this delay. Otherwise, use the normal block delay. These things have been tweaked so that they're a little smaller. Meanwhile, right, delay before delivering, that could be true or not. So that's been enhanced. So there's not much going on in the planner, you can see. The planner itself is doing a little extra. It's just changing the delay before delivering bit. And delay before delivering, as I recall, is, I forget what we used it for. This is an old one, but we had an issue where if you sent two small moves, like it would finish the first move before, you know, and it wouldn't get a chance to chain them. Or even any two moves. Anytime you sent two moves, it would start the first one before it ever chained to the second one, and so the motion would be wrong. It would actually do a start, stop, and continue. That was a weird one. We had to figure out some way to deal with that, and I initially just split the first move into two, so it would give it time for the next one to come into the queue and then chain. And we tried some other things, and I think we ended up with this new solution, which was delay before delivering, which is like some number of, block delay for first move. We called it, and it was 100 milliseconds or something. Yeah, it must be less than 250. It says it's, it must be less than 250. But basically, it was a way of, when the planner's empty, to make sure that it gets at least two moves in it before it starts, you know, chaining things and doing the motion. Otherwise, you would have some issues. So that was enough time. Meanwhile, Stepper had a slight change, which is abort current block. Got moved into public. I actually switched it up and made it so that FXDI control is now a friend class, so it can be private. But the other things that it's doing is it has a block queue update call. It has a thing called Stepper for applying direction and command. We'll look at that. And then a thing for refresh axis to move. So it just refreshes that flag. So this particular one, block queue update, is actually taking over the planner handling, I guess. So we'll look at that in a moment. Meanwhile, in Stepper CPP, you'll see that this new input shaper is, again, it's giving us this command skip count variable. It's giving us a step command ready. So it was loaded from the buffers and is ready. So there's some interesting things going on there. Apply direction, which is just a flag for whether or not direction output needs to be set. And we have a step command. So there's a step command to be output. A next aux ISR, so there's an auxiliary ISR, spelled in the Canadian manner, I guess. And in Queen's English, baby, or King's English now, I guess. Meanwhile, there's this whole separate bit inside of the Stepper ISR. And as you can see, it's quite unique, but not huge. Again, you know, we're always surprised by the small amount of code that's required for adding this feature to Marlin. Although we'll be looking at the fixed time control files in a second, but As far as the stepper goes, it's basically receiving a new type of ISR to handle, and it's still using the ISR step logic to a large extent. It's just coming up with different ways of setting the timing, and then it's getting its signals from a different place. So what's interesting about that is we still have, stepper step, all that stuff. You won't see anything in here where it's actually doing the stepping part, where it's setting stepper pins until you get to here. So this actually is taking over the stepper control, which is very interesting. So we'll be looking at that a little bit. But in the meantime, you have, let's see, that's called, what is it? FXD control underscore stepper. So it's just the thing and stepper. So as we go up here, we'll see it gets called where? I'm assuming up here. Again, mostly I've just been cleaning this up. I haven't dived deeply into it yet. So you're along on the journey with me here. Together we shall explore. Meanwhile, let me pull up the old Discordians, just in case. Live. So yeah, and I'll just go to the old live stream channel, and I'll even share my screen, because that's just the nice thing to do. Okay, good to go. So yeah, we can look at this in the editor to get a little more of a clue of what's going on. What line are we at? Oh, 1480 or so. Let's just jump down to there. All right, so yeah, here you can see this is where I've cleaned it up. So it's a little different from what I was just showing you here. Cleaned up a bit, but otherwise mostly the same. Certainly the logic is all the same, I hope. You never know. But anyway, so as you can see, there is this new bit down here. I'll just use this to find my pieces. So yeah, FXDI control stepper at 3078. And these will become const. I see all kinds of little tweaks I'll be making, and there's also this thing called block queue update. And I'm going to document the heck out of these things. One of the things you can see is that it's doing the standard stepper stuff. And it's amazing in Marlin how much it's been simplified to the extent where you can just say, okay, we know all the steppers pins now. We know, the timing was all been, predetermined by your configuration and type of stepper driver you're using. And so we can just use these little macros that are set up to do the stepping. And as long as those are good, we're good. And you'll notice that this particular thing it's set up to only do Cartesian with a single extruder at this time. And it has its own handling of linear advance. So that's where it becomes a little bit tricky. I would really like to take this and make sure that it is integrated as much as possible. One of the things that we found with the current input shaper, hey Gary T, congratulations, happy Sunday, welcome. We are delving, so sorry to be already in the middle of this, but here we are. So one of the things I'll have to do is add the extra axes, deal with their pulses, and or move this stuff up into the regular handling of stepping, and consider how that might be done. One of the things with our current input shaper I was going to mention a moment ago was that we have this slight delay between the X and the Y shaper. Like it'll do a step on X and then it checks to see if it needs to do a step on Y, and it'll do a delay for one or the other. But if those pulses were handled up in the same section with the other pulses, using whatever kind of logic we have to, then we could eliminate that little extra pulse delay and save, a lot of it amounts to a lot of time spent inside the stepper ISR, which we really want to get out of as quickly as possible. So that particular move of the code from there to there is going to be a challenge. But right here, the branch I have open is not, let's see, this is still built on 2.1.1. I have a branch that I started building on 2.1.2, so it actually has both shapers in it. So you could say, you can't enable them both, but you could enable one or the other and pick the one you like better, the one that performs better with your hardware, or the one that, has the shaper that works better for your situation. We don't want to make like a zillion options. The real reason for keeping the current ZV shaper is that it's just so low impact and doesn't require as much overhead that we can actually employ it on an AVR, which is amazing. So that alone is, a reason to keep it, if only to show off how cool we are. But yeah, as you can see, there's like, this thing is like, what Z-dar, do we need to do Z direction? And as you can see, I've already wrapped these up saying, yeah, if you have a Z axis, do this. If you don't, you can't. So I've started to do that kind of stuff here. And yeah, as you can see, this is very much limited to a single extruder Cartesian machine, essentially. Maybe a core XY, maybe a delta. I don't really know yet. I really need to look at how this all works before I fully understand how much it can be employed for those types of machines. DeltaBot is obviously a weird situation because it's moving this effector like this, but at the same time it's all happening with motion like this. So if you're creating smoothing on a motion that's going like this, that's good. You've got your little arms are not going to be shaking as much, and that's really where the energy is getting exerted. As you move a belt up and down, it's creating this resonance in the towers. But presumably, depending on the type of linkage you have, it's going to be whether it's wheels or linear rails or whatever, you're going to get different kind of resonances. And sometimes you can get some binding that you obviously want to avoid. But even the best motion systems may have binding when you try to move too fast. So yeah, it gets weird. Meanwhile, we have this block Q update, and so this is actually looking at handling the Q part of it. And then we have refresh axis did move, and then that takes care of all the flags and setting the flag called axis did move, and basically setting which axes did move. So that's pretty cool. And it says here, it debounces the axis move indication to account for potential delay between the block information and the stepper commands. Good. Yeah, this is something they had to do to fix an issue. I ended up going, and this was multiplied by 0.0025F previously, and I made it, or divided by, so I just said, well, that's multiplying by 400. So I just did that to hopefully speed things up a little teeny bit, even if it's, which will help. I assume that it would be multiplying by 400, but then rounding, and you don't really need to do that. This is a, it's an integer. So clearly we don't need to divide it by 0.0025F if we can just multiply by 400. So yeah, various things, has Y, has Z. I had to wrap it up in that. So again, pretty straightforward. Here's the block Q update, which I skipped over real quick. We'll just take a quick look at this. What's going on? Get block proc dn. I forget what done, I guess. Get block processing done. Okay. I think I would go with is block processing done. Just spell it right out. And you know me, I'm also going to change all these from camel case to like whatever this is called. Underscore case? I don't know. Dromedary case? But yeah, I just find it easier to read this than that, if you don't mind my saying so. So little things like that will get changed style-wise. I don't want to do too much of that if we're going to be collaborating a little bit on the implementation with Ulendo. I feel like they've done so much already, but if they want to come in and contribute little tweaks, I don't want to make the code look too foreign before they get a chance to have a look at it. That's why, again, this is one of the main reasons I've preserved this set of like little tweaks, or lots of little commits changing one thing, one other thing, is just that it's easier to see for each given thing like what I've done. It just makes more sense in collaboration to keep these things very clear. And if I made a mistake in any one of these steps, then it should be easier to catch than if I have it all in one big blob, which is what I did with my rebase. You can see it's all like, first there's this bit, and then boom, it's all one big blob, so it's already cleaned up. I have to be careful to match the cleanups I do in my little work branch with my rebase branch, but I'm kind of like on this, I think I'm pretty much done with these, and I'm going to move on to using bug fix as my basis going forward, so I have something which has both input shapers and I can do better, more comparisons and stuff. So yeah, pretty fascinating. All the things we have going on in this new motion control. So let's take a quick look at their addition called fixedTimeControl.h in CPP. So you can actually get a closer look at these here. Yeah. So among the various things we have going on is the different types of motion control. So we have all these, and they all have, little integer representation. Anything between here and here, under 20 and over that, is a type of thing. And also there's this thing called Ulendo FBS, which by the way is not here. So don't get your hopes up, but that's filtered B-spline. And filtered B-spline changes the curve of the acceleration curve to give it a little bit more like of a gentle acceleration at the start and end of moves, and even on direction changes, so that you get a little less of a jerk there. And it's sort of it's like S-curve acceleration, but a little more comprehensive. I happen to think our S-curve is more or less just fine, because it has, it smooths things out, and I don't know how, down and detailed you really need to get with that, Anyway, let me fix these up. One of the things I like to do is make sure that macros like this are wrapped up in case some wisecracker decides to put I don't know, something like a ternary expression in there. We don't have to worry about that causing issues with the multiplication. Like only the last thing gets multiplied or whatever. As you can see, I've been doing this bit where throwing in a little default just so we can leave it out if necessary. And also to give some clue this tends to be self-documenting in a certain way. If Zeta uses this, okay, good to know. Meanwhile, yeah, so you can see there's a lot of little variables this thing uses, and we may think about changing some of these if they're if they use up too much memory or whatever. I don't foresee a huge amount of memory or it being a major problem to have lots of memory usage for this feature, since it does also, as they've told me, require a 32-bit board. It's quite demanding compared to our little modest ZV shaper. And as you can see, there's a lot of int32s here and so on that come into it. And so those can be faster on some processors than than maybe 16-bit. It really depends. So, but I'm going to look into that and see whether there is any optimization to be gained from reducing these variables in size when they don't need to be 32 bits, or if you get extra overhead from extending them, sign extending and things like that. Those kinds of things can slow it down, so it really needs to be profiled carefully. So So anyhow, yeah, all kinds of stuff is going on with these. And I think what I'll also end up doing is, yeah, as I mentioned, I'll make it so you can enable or disable the shapers you want to use or keep or compile in. And that can save a few bytes and definitely improve performance because there's less logic going on to figure out what shaper you're using. And also, if you have a single shaper enabled, then you can skip that whole blob of logic and again get that better performance. So as you can see, most of this is just variables, and then we have the actual functions. And apparently there are public ones and private ones. So let's take a quick look at the public ones. So you've got one to start the block processing, set controller states to begin processing a block. All right, good. Get block processing done. Again, I'm going to change the name of that. Return true if the controller no longer needs the current block. That's their controller, how it is meant. And then we have this one, which is run out block. Move any free data points to the stepper buffer, even if a full batch isn't ready. Interesting. So yeah, basically it runs out the block, or say completes the block. They're calling them data points, which is interesting. Which, is a good way of visualizing input shaping, I guess. There, of course, is this which is called from idle, which, yeah, it's basically continuously monitoring the current state and doing whatever needs to be done. And again, this can be interrupted by a long display update of some kind or whatever, so we have to be very careful. Any kind of, like, our idle procedure is calling so many things that, if you had like lots of features enabled, like there could be a significant delay between these loops. So hopefully it doesn't need to run, like every cycle or anything, but it just needs to run at a reasonable speed. So again, we'll profile a lot of these things and get some sense of where we can localize these, if we can localize them in better places. Meanwhile, we have this update shaping A, which refreshes the gains used by shaping functions, whatever those are, to be called on init or mode or zeta change. So basically it's updating refreshes the gains. I'm going to try and find a better word for that, because I think gains is, I believe it means something like, it's kind of like volume when you turn up the gain on your, so it's more like amplitudes, I would say, something like that. So maybe amplitudes is a better word there. I'm not sure yet. We'll see. But zeta and VTOL, so-called, will be interesting to study and understand. Input shaping as a thing is kind of like, it's well understood by your mathematicians and your motion people and your theoretical types. I aspire to be that smart, but again, I definitely missed my moment to get in early in engineering and wrap my head around all this stuff. So at my advanced, elderly age, I have to be, it takes me a longer time to get it into my head, but it's getting in there. It's getting in there slowly. This thick head will eventually, some of it will sink in. So meanwhile, you have some private functions, methods. I like to call them methods, just because I'm a C++ geek. And interestingly, I did not fix the indent in here, or did I? Oh yeah, I guess I did, because I like my privates and stuff to be, let me rephrase that. I like my private section to be indented a little extra, even though outdenting makes it look prettier. Gives you a little more space. I may have to describe what these are doing. So stepper command buff items, whatever. There's your init, of course you want one of those. Load block data. So I guess, I'm not sure whether that writes into the block or reads from the block, but we'll see. You could also do this, just to say that current block pointer isn't changing. And we can see what all these are doing eventually. So yeah, we'll be looking at these in a second. Make vector, interesting. Why do we want to make a vector? And convert to steps, which is fairly straightforward. Let's look at that one. That's kind of interesting. There you are. So it takes an IDX, whatever that is. I see. It's looking it up inside of our XM. And yeah, we're going to be looking at these and figuring out what that's all about in a second. I have changed some of this and modified it from what they originally had. So sorry, Ulendo guys, it is a little different, but I was just tweaking it to kind of put const in mostly. So you have, yeah, all kinds of interesting things going on there. And then I set it up so you could use this or that instead of commenting one out and having a thing where you comment one in and comment the other out. I just made a little private defined so you can choose which one you like. And, you know, that'll make it a little easier. I'll put it down here where it's easier to, right next to the thing, where it'll be easier to see. So, yeah, what else is happening in this? Well, not a lot that we can understand yet. You got shaping variables. There's 5, you know, XAIs. There's 5 XNIs, and then the same for Y, and so on. Now, you can conceivably with this, we could shape, you know, X, Y, Z, I, J, K, you know, all the axes could get shaped. I believe right now we're just shaping X, Y, but we could certainly, you know, for your 20-axis robot arm, well, I guess 9. If you're a 9-axis robot arm, we could definitely, you know, extend this to do shaping for all of those. The ZV shaper that we have in Marlin currently, 212, is definitely really meant to be limited to XY and doesn't really need to be expanded, although if it were expanded, it would also tend to be more efficient than this, just because of the way it's, you know, set up. Although we're going to have to definitely do something about those, that extra pulse delay in there. I'm really anxious to do something about that extra pulse delay, generally speaking. Like, for example, if you know that, well, you have to do on and off at some point. You could, and if you do like off just before, I mean, at some point you have to have a delay. So it kind of is like, it would be nice if we had the option to call the stepper ISR or some other interrupt to turn pins off, or if there were a built-in hardware option to say, oh yeah, I want this pin to be set in hardware so that when I turn it on, it automatically turns itself off after X delay, and I don't have to touch anything. And you could do, I mean, that would be a great feature in a hardware or in a board. If anyone's thinking about something like that, all it is like basically it's a timed latch. And if there were a way to program a timed latch on a board, even if it's, you know, outside of the MCU or whatever, it would still be like, it would be very cool. Then we could basically get, you know, way better performance because we wouldn't have to sit around on the ISR and wait for the pulse to turn off. We could just turn them on, and then we would know they would be turned off at the right time sometime before we come back and turn them on again. So that would be handy. Anyway, yeah, lots of UN32s, lots of floats, which I guess are also, we definitely don't want to use double, although we may get better performance from FPUs in some cases. And of course, because there is a lot going on in this, from like the idle function, or I should say the loop function method, whatever I want to call it. This is getting called from user space, so it should be able to use the FPU. So if you're going to do any major, you know, floating point math, this would be the place to do it. Meanwhile, we have this kind of thing going on. So yeah, let's take a quick study, make a little quick study of what's going on in this input shaper. And maybe we can take a look at our own input shaper and get some sense of how it's different. So again, there are various things that have changed, which only those who are looking at the original code are going to care too much about. Getting rid of stuff when there's no y-axis and so on. Carrying on. So yeah, these are your storage. Initially, you have XD, batch size. Let's find out what batch size is about. So 100 is a batch size for trajectory generation. So that sets up, arrays which are going to be, so if you set it to be 100, here you've got a float, you've got 100 times 2, 200 floats, and another 100 floats right here. That's just for X. So you got 300 floats, which is 1200 bytes. So for each axis, you got 1.2 K, KIB, K, I forget which KB to use, but it's, and then you've got another one. So yeah, you're looking at like 6K of RAM for your, it gets pretty ridiculous. What did I say, 6? About 5-ish. And then, I'm assuming these other buffers up here are also going to take up a good amount of space. For example, stepper command buffer size 1,000, but it's only 1,000 bytes. So, there may be ways to speed this up too and make these smaller. For example, we could use a kind of bit shifting scheme where the commands are only 2 bits wide or whatever, and then, we just shift along and look at each set of 2 bits, and that would make it, 4 times as small, which would be nice. So we can figure out some ways to do that if we need to make these more optimal. And again, these are also sized for Ulendo FBS, which again, I don't know how much of that FBS is in here yet. It's commented out, or it was commented out as an option, so I don't, let's take a look here, yeah, see, it's all commented out in M950, which just means you can't set it that mode, I guess. Only, yeah. So right now it's not in there, which is fine. They can keep that kind of stuff private. The rest of this stuff is really cool though. So, and we have our S-curve, so maybe we can get that in there somehow along with this. But this is very much its own stepper. It's quite astounding how much it is its own, self-contained thing. Let's fix those indents, shall we? They were originally indenting with, I think, 4 space tabs. So I just want to make them all kind of fit where they're meant to fit. That'll do. Dabble, do ya? Okay, and fine. Fine, we'll line them up. So yeah, these kinds of things, N1, N2, do we need it? Yes, we do. Yes, we do. And then, how much is it used? Interesting. We'll figure it all out. Some of these, can be localized as well. They don't necessarily have to be static data members. They could just be statically included here. And that would make them super private. But I guess it is nice to expose them in the class so that if you feel like getting down with debugging, you can have an external thing. Make it a friend class and go to town. We'll see how that all comes out. Meanwhile, yeah, so you've got, as I'm zooming down, sorry, we should take a closer look at some of these and see what's going on. So of course, config mode is, what kind of mode are we in? Are we in, fixed motion mode, or are we using regular Marlin motion? That's the other cool thing, is you can switch out of this and just use regular Marlin motion. So if you don't need the advanced input shapers, you don't want to use them, or you don't have the room to use them, you can still go back to regular input shaper, and you can actually turn it on and off, which is pretty cool. We don't usually have that for things like this at this low level, so that's kind of neat. Although it is, it does mean that for every motion, it's going to be checking, hey, what motion mode am I in? How should I be doing this motion today? So it may, create a tiny bit of overhead in every ISR, which, you never really want. So if you're never going to use it, I recommend turning it off. So yeah, this is interesting. Index of next stepper command write, index of next stepper command read. So this is a circular buffer thing, I assume. So we actually have a circular buffer kind of class. So one thing we could do here is to wrap this in that and use that instead of having this be you know, produce, consume. It really should be head and tail, I think. Hey, Mr. Gremlin, what's up? What's up? Meanwhile, sorry, I don't mean to misgender you if I'm doing that. Ms. Gremlin, Mr. Gremlin, Madam or Sir Gremlin, Lord or Lady Gremlin. So here we have, yeah, lots of memory being used. So, you know, avert your eyes if this frightens you. It certainly frightens me to see that many. So then, of course, null pointer. Hey, they use null pointer. That's a plus in my book. We often forget in our C world that it's supposed to be null pointer and not null. So yeah, check it out. You got your pointer to the current block being processed. A block is ready. A storage for the previous indicator. I don't know why it's called Z1 or Z1. Then you have, is the block procedure done? A little flag for that. Is a batch of the fixed time trajectory has been generated and now available. So that's pretty cool. And it sort of implies that there's one, it's going to go off and do this somewhere. And then we need a flag. And we're avoiding, we got to be careful with race conditions and with things like that, of course. The batch is being post-processed. Is that what this is? Batch is ready, not just ready, but ready for interpolation. Run out of the block hasn't been done and is allowed. Neat. We'll see what run out's about. I assume that just means it's like, it's going to churn through whatever is in the block. Then you have some interesting things. Total movement length of a block. Cool, that's unique to, that kind of goes with the trapezoid. Then you have these for each axis has its own start position, end position, as it were in the previous block. So I'm going to actually, I think this label is incorrect. It should be like end position of previous block. But it is millimeters. And then an axis move ratio, which is no unit, of course. It's just, you know, the proportion between x and, I guess I assume, the total length, I would gather or guess. We'll see. So the same thing with y, z, extruder. Then you have, of course, your acceleration prime, deceleration prime, and we don't need that to be on right now. Starting feed rate, position after acceleration phase, pretty interesting. And that is, again, what is a position? I assume within the total length or within the total steps. Position after acceleration and coasting phase. Yeah, so that's like what we use in our trapezoid. We have like an acceleration length, and this one is millimeters per second, so that's actually acceleration. This is deceleration units. And that's interesting. The acceleration prime is interesting. That implies that you have this kind of like pre-acceleration, and then you have like this dude. Hey, dude. Yeah, well, I had a friend who just hated to be called dude at one point, and it was funny. I was like, I was such an awkward kid. But we were out on our little drive to go down to like Providence, Rhode Island for a book signing. It was Clive Barker. And Clive Barker called him dude. And I was like, hey man, don't call him dude. So yeah, I made Clive Barker feel awkward, but you know, I do that. Anyway, call me a partial fan of Clive Barker. I think he's great, but also a hack. Is that possible? He's a great, but also a hack. Like I am. I'm great, but also a hack. So we're on the same page, me and Clive. Anyhow, here we have we have our, yeah, so we've got all these things going on. So that's your trapezoid stuff. Makes sense. Now we have N1, N2, N3. I don't know what those are. Number of data points. Okay, again, more trapezoidal stuff. Happily in UNT32s. These, if they're steps, I guess they're probably not since they're floats. I assume these are then going to be millimeters. So we'll look them up and see what the unit is. As much as we can do in steps, we should definitely do as much in steps as possible. I understand you definitely have to do certain things in floating point, but there's also, we have the possibility of anything that's dynamical. I'm going to use that word, dynamical, because I just like the extra syllable. The dynamical elements, anything that's dynamic, we can use a Bresenham approach or a rational approach. Where you have, top and you have, and also it's modal, a modal rational Bresenham approach. Every time the thing rolls over, you accumulate by one, but you're rolling over in terms of a proportion. And so the rolling over happens at irregular intervals, but overall it comes out semi-regular. That's the idea of Bresenham, is dividing things up in a dynamical way. So if we can do it in a Bresenham way, and I keep coming back to that for our other input shaper as well, like anything we can do in a Bresenham way where we don't need a big buffer would be really cool. And I have been thinking more about that as like, okay, if you had a time offset for a fake axis, so you make a x-axis and then you have an x-shaper axis, and then you have, you're generating the steps as if it were just another axis, but it's set up in such a way that it's doing its Bresenham counter exactly offset by, X amount of time from the previous one. And presumably everything is very deterministic in Marlin. So, except that we don't necessarily know how much time things are going to take within the ISR, but we do know that we want to come back to the ISR at as close to the right moment to do this next step as possible, which is why we divided up like the pulse phase from the preparation phase. So we have like this, setup phase, which is being called periodically, and then the pulse phase is called at a higher priority, so that it's already, things that are already set up, great. If it's not, we'll spend the extra time to do the setup for the next time around. And that's worked out really well, although I can't say it's like perfect, but it's not bad. It's not bad. I know we can probably do better there. So that's kind of a vague summary of the theory that we have going. Our little motion theory. I like to call it motion theory because it makes me feel like more of a computer scientist. I'm a computer scientist, man. I'm a software engineer, man. So yeah, some pretty cool things. This not set, I might just call that unset, just to save that one extra space and get my comments moved over. Interpolation variables, what are they? And what is vector variables? We're going to find out in a minute. You have this thing called make vector index, okay? Index of fixed time trajectory generation of the block. I get you. Fixed time trajectory generation. So you can think of that as the slope, I guess. The slope intercept, where your intercept is your time and your slope is your trajectory. Then you have the previously calculated index above. So there's a need for that. I believe that's so you can compare or contrast or do some math between the two. Then you got this thing called the batch index, index of the fixed time trajectory generation within the batch. Good to know. And we'll figure out what's going on with that in a bit. Meanwhile, interpolation variables. What's an interpolation? Well, it's a step count accumulator. And it's a direction state, so you remember which way you're going, left or right, forward or backward, minus or plus. Although dir state is, it's got an enumerator. So I'm actually going to change some of these to be the enumerated values instead, but it is positive. So y is +1 and -2. I mean, it could be -1 and negative could be +1 instead, just so it would be, you could also use them in another way if you wanted to. But for now, it's a three-step thing. It's not set or it's positive or negative. If it's not set, it's indeterminate. And you could also say positive and negative are also, on a certain level, indeterminate because we don't know whether it's high or low. You know, the logic of direction could go either way. So fascinating. Anyhow, so yeah, you've got step count, you got a direction state. Good. You've got index of current data point being interpolated. Okay, data point. Again, previously calculated, and next is the accumulator for the next step time. And that's actually HAL timer T. Good. HAL timer T, by the way, it's just a number. It's either 16 bits or 32, depending on how wide the timer is that we're using. And on AVR, it's 16 bits, and always 32 bits on other things. And then we've got shaping variables. How much is Zmax? Another 100. So we're looking at another 100 floats here. So that's 400 bytes just for X, another 400 bytes for Y. So yeah, we're looking at a good, 6K of storage for your typical shapers here. Which again, got the space, great, but some boards just don't. So we may find ways of optimizing this, or we may not. We'll see. The work by Tom is really good in the amount of optimization that was achieved. They could, at one point, cut the amount of storage in half. So that's pretty good. And I bet we can, again, if we could get that Bresenham counter in there, we could get rid of the RAM usage entirely, almost entirely, down to like 10 bytes from 100 or 1,000 or whatever it is. We could definitely, that would be really cool. And I can see ways to do that, but the way we reckon time, I think, is relative in this input in the stepper. So it's like, it basically has like, when is the next one going to fire? We reset the time to 0 and then use so it can never like overflow. And if it did overflow, or we set it up to do, I forget exactly, but the way you do interrupts and stuff, you can do them off of a counter that reaches a threshold. So it counts from 0 to 50. Once it reaches 50, it fires and it stops, or maybe it resets to 0 automatically, or maybe we have to do it, reset it to 0 ourselves. It all depends on how it's set up. And we have different options for different timers. There's like a real-time clock that you can use on some processors, even some AVRs. So we just have to pick the best timer for the job. So these are interesting here. Your shaping variables, you got 100 of those, you got 5 of these. And these 5, I assume, are the factors, the A and the N we saw above. Input update shaping A, update shaping N are related to these. So we'll find out more about those soon enough. So yeah, if you've got X, you're going to be using 400 and here's another 20, so 480 each, it looks like. Another 480 here. Or 440. And then here we've got these that are always used. Even if you don't have both X and Y, it's still called XY. And it may turn out that when you only have a single axis, or if you're only shaping a single axis, might not need to even use these. We could just use one of the others that's counting up or whatever. Like the max of XY is just going to be the X. If there's only X. And the index, well, we'll see what that's about. ZI index. Index of storage in the data point delay vectors. So, boy, we're definitely picking up some new vocabulary here. Data points, vectors, we'll see what those all mean in terms of how this works. A vector is really just, it's a set of numbers. Or it could even be a single number. It depends on how you're utilizing it. And sometimes vector can, I don't know, is it trajectory? We're using the word trajectory to mean like a slope or whatever. Meanwhile, linear advance, so actually, as I mentioned, this actually implements its own linear advance. So it's using its own linear advance options and settings. So if we can match up ours, like the ones that are in linear advance, and just have this, the regular linear advance values get translated to whatever this uses when it needs them, that'll be good. I know it's a different linear advance, and it's also, well, we can look at how it works, but I assume it's on a similar level. So anyway, here we are, functions, public functions, or methods. So starting right away, start block proc. So first off, we copy the current block that is sent to us. Then we set this thing to true. Yeah. Yep, someone's in live stream. Hold on. Switch it over.
Hi.
Hey. What's going on? I'm turning this user volume down because he seems to be in pain. Meanwhile, block proc ready is true. So I guess that means we're ready. Done, nope. Run out enabled. Sure, go ahead and run it out. Apparently, you can run it out, whatever it is. Moving on, let's learn. We've done very little here, so that's nice and simple. When is this called, by the way? It is called in stepper CPP as part of when you've got a new block. You got a block. We passed up we handled sync blocks, we handled laser power blocks or whatever, power blocks. And then we saved our direction bits, and then we call fixed time control to let it know about the block. So that's what's going on there, very handy. And then if we didn't have a block, like there are no blocks basically to get at all. It just runs out its own block, whatever it had. So that's interesting. And then returns. So it's totally done at this point. Also, that's kind of redundant because we're not doing anything else in this method. So we don't necessarily have to have that. But also it's part of this. So, oh, I see. So yeah, this itself is being called from, it looks like it's being called from the loop. Oh no, it's being called here. Yeah, it's being called from the loop. So yeah, we'll learn more about that soon. So as you can see, one of the things the loop does, of course, is if you're not enabled, it just exits right away. That's pretty cool. So we have that, and we have the other thing we were looking at. Start block proc. Okay, so is the block procedure done? It just returns the flag. Simple enough. And this could actually be inline in the class, which may optimize it slightly. It depends on the compiler and the flags set on the compiler. But as far as I understand, these kinds of things do get inlined even when they're inside a CPP file. But it may depend. This is compiled as a separate unit, so yeah. I would say I'll probably, for optimization purposes, I would make this an inline. Just for the slightly better performance. Yeah, if you have comments or anything you want to throw in, I'm going to open up the chat view in here, and you can throw me some text because the audio on my on this thing sucks. There we go. Last comments were from January 6. All right, so yeah, if you're on Discord in the live area, throw up a comment and let me know. I'm going to figure out ways to channel the audio from like Discord and other apps into OBS. I'll probably end up getting audio hijack or something like that if I need to. But I may just be able to install like the Jack plugin or something like that. We'll see. Anyway, studying, continuing our little study. So we have this thing called runout block, and this is called when a block is ready to be run out. So let's take a look at when that's called. And sure enough, it's called in Stepper as part of the block queue update, which is called from the user thread loop. Very often, basically just very often. What is the most often it'll be called? We have to figure that out. And just give it a little profile and see how often it does get called. I would be curious to know. And we can probably start throwing in profiler code for things like that. One of the things I would like to do is definitely have like stuff in the ISR where we write into a big old buffer and then we can examine it later. Even though it may add a tiny bit of overhead, it'll give us some idea of the timings that are going on. So we basically store like, what's the current timer value or how much time, between things, and then stick them in a big old table and just use a big old circular queue. And then we can examine that either in the simulator or wherever, attach an ST-Link and really get a close look at that as it's actually running. I would like to know for sure how much time things take and get that profiled as well as possible. We have all these sort of assumed numbers of ticks, which is processor ticks or timer ticks for any given thing that we use to kind of pre-calculate and estimate and guesstimate. And they may not always be great, and that may be part of why we're getting that extra throttling in the display or in certain displays now. So Chris, who was it? Not Chris Riley, 3D Jake, in his review of our input shaping or initial look at our input shaping, did encounter that. And so that is something we definitely want to solve as quickly as we can, for our reputation. We gotta make sure people know we geniuses. Meanwhile, we don't even know fools. We know what we're doing. So you have this thing, a run out of block. Is it ready to be run out, and is batch ready? So this says right here, basically it sets batch ready in here to true, which means that it's ready. I am presuming that this won't get called again, but we do have to be careful about that. Again, idle can be called in recursively, and we don't want this to get called recursively, so it may make sense to just put this up at top here, and just in case, just to say it, just to give it that this little bit of extra time right here. But the thing is, this isn't calling idle, so it should be okay. Nothing in here is, so we should be okay. If there was anything in here where it was like waiting or whatever, we would probably be in trouble. The other thing about this is, is this the fastest loop variable, and is the batch size really that big that we need 32 bits to store it? I don't think so. So, we should use the smallest variable we need to here, or at least I would say the fastest one. Oops, 16. The fastest variable we should use. And there's actually there's a thing called fast underscore. There are these fast types, and then there are these, I don't know, there's fast and small, I think. And so you could say, I want to use the fastest integer for this, please. And it'll give you the integer's size that the processor handles most quickly. And again, if the processor needs to do weird sign extension or anything like that, that's where it makes sense. So what's going on here? We've got, all right, so through this, we have this thing going in a loop. It's copying from xdi equals the batch ID x minus 1, which is interesting. So I see if it's greater than this, then it can copy the last item So what is going on in this? We don't quite know, but we'll figure it out. And then at the end of it, it says, okay, we're now this, which means it's not greater than this anymore. So next time it comes back, it won't, until it comes back, or until this changes, it's going to be skipping this loop. It says the batch is ready, which is interesting. So pretty fascinating. And then, of course, it's ready. And then run enable is false, which means that this has been done, and therefore it needs to be set up again if it's ever going to do this. So great. Now you'll notice that I could do if not run not enable and batch ready or batch ready return, and it would be fine because this is already false, so we don't need to do this. Or I should say, let's see, this is always going to be set false, and this, by the way, is always called from hoping not interrupt context, just for the sake of what's going on. Yeah, it's being called from, again, from the loop. Which is, again, it's user space. So the main thread. That's kind of cool. Anyway, we're about to get to loop. We're about to get to the loop. So very fascinating. Runs out the block. Basically prepares it by copying. It's interesting. It's going through the whole batch size, and it seems like this would actually overlap it, though, doesn't it? Or does it? If it's greater than this, then do that. Y is less than twice that. Oh, okay, it makes sense. So it's like the second half, basically. So if you're in the second half of the batch, then you can copy this one item repeatedly to the first half of the batch. But it's actually twice, which is interesting. It kind of implies that it's going to be copying it twice. This may actually be doing too much. We'll have to look at how it works. It's fascinating. See it in action maybe once I get it in the simulator. Here we have loop. So this is actually called from idle. If we're not doing any kind of shaping, if we're not using this particular fixed time motion, then it returns. What's also interesting about this is, yeah, we could make it so that you always have fixed time motion, and then it would like not compile in any of the stuff that Marlin is doing for motion, like its previous motion code, and that would save some space. We still fill in blocks. This is really the cool part about this, is it is non-disruptive. That was part of their goal in implementing this, was to make it non-disruptive, which is pretty cool. What's also interesting about this is that it does this init thing here, so that every time it's called in loop, it's also checking to see if it's initted already. Calls init, and if so we could conceivably do this in another spot. Like Marlin could have a pre-init that follows from that, but also you'll notice that like this only ever gets initted when the first time you use it. My thinking is that, yeah, you probably get away with just initializing it in the setup, and we don't have to do this here. So that's a little extra overhead that we can get rid of. Meanwhile, are you supposed to abort the current block? If so, we're going to just skip it. So that's one of the things that we flagged that is now shared with this class. Pardon my yawning. I'm getting like 6 hours for some reason. It's my favorite amount of time to sleep these days. So Yawn. So yeah, it does this thing. And then if the stepper is busy, return, which is interesting. So it has its own stepper busy flag up here. And normally false. It has items and is in use. So when is that set? Let's take a look. It is set here. When there's data in the buffers. Good to know. Okay, so what does it do next? We have a reset. And reset, as we saw, simply resets a few flags. What's the current block? Oh wait, no, that's not reset. Where's reset? Oh, it does a lot. Okay, so yeah, reset. If it's doing this fairly often, then we may be able to get away with doing this less. Or we can optimize it in various ways. But essentially, it's setting a bunch of the flags false, a bunch of indexes to 0, resetting its own little circular buffer. So again, we could do our circular buffer thing more simply and call its own reset. Here we have it's going through the batch size and resetting x, d, y, d, z, d, e, d for the trajectory history. Okay, good to know. This and then set some flags, false, and again some things, the previous block stuff to 0, and various end positions, which we'll learn more about. And it's setting these to 0. It's setting this index to the batch size, which, as we saw earlier, is special. Then a bunch of things to 0. Again, more zeros, indexes for the vector, for the interpolation, and of course our dir state is now not set anymore for any of the axes. These I really am inclined to make into an array. Since, it's always going to the same array element. Like if I make these into, I think it's XYZ type, it will have all the axes, and then it would make it possible. That's kind of the reason I made those types, was so you could just say, oh, just give me this type and it'll represent all the axes, and then I can refer to the ones I want. I didn't set up types that just do X, Y, Z, and E by themselves, which, would be easy enough to do. I could set it up as a type just for this class here if I needed to. But it would be nice to have shapers on all the axes if you really wanted to. I guess I would want to, have it be selective and just say, oh yeah, just give me the ones that I need for the axes that we're using. And in that case, using separate variables may be the most simple, clean way to do it. Either way, this is very much built around the assumption that X and Y are special and Z is not doing shaping. Although, you could imagine a case where you were doing core XZ or something, and then you might want to shape your Z, I don't know, to match the X. Who knows? Who knows? So you have that. Here you've got it resetting this XD and YD ZI. So, okay. Very good. So then it's doing all that. So then, of course, it's also telling it, hey, we have done the abort of the block. It's been handled here. That's pretty cool. I do wonder if there needs to be a method to set this. We have a thing called quick stop, which is the opposite. So yeah, I would say abort current block is false when we call discard current block. So yeah, it's basically doing what the fixed time is doing, but in its own special way. We discard current block just by skipping it, change the index or whatever of the block, and that basically skips it. In this case, they're calling reset to do the skipping, which basically is like just don't process it. So if not block proc ready, block queue update. I assume this can be set, the block proc ready can be set by this, which is why it's then checking it again. But we can certainly look at that. Just make sure that it can. Current block, current block, current block. Variable we're looking for again? We're looking for this one. Yeah, so it's, I assume it's ready when it's done with this thing. So, but, whoop, it's not actually set here. Who sets it? It seems to be only set in the start block proc. Okay. Good to know. But that is called by the stepper. So yeah. Good to know. Continuing in our loop, what else happens here? All right, so we do all that, then it sets this, and if that's not ready, then we have to do this thing, load block data from the current block copy from earlier. So yeah, the order in which these things are happening is always, you know, tricky. Always tricky to keep track of that kind of stuff. Moving on. So yeah, while it's not done and not ready, and this index minus that index, which I guess this is always going to be greater, is less than, or maybe always tend to be greater, I guess, less than the points per loop. Good to know. Points per loop, 100. Then keep making vectors. And let's see what make vector does. That's kind of interesting. May have to do it this way. Yeah, there you are. Ooh, make vector. Let's see. Generate data points of the trajectory. You're witnessing my mind being blown in real time here. What does what now? Oh, I see Shepard's in the live channel. I've got everybody kind of, well, I had somebody muted. Or at least turned down because it was getting a little bit weird. But yeah, if you want to drop a comment anywhere, I will answer your comments or questions. So yeah, fascinating. Make vector. So make vector, generate the data points of the trajectory. Okay, tau. The tau is index plus 1 times TS. What's that? TS is our time step, which is 0.001F. That is to say 1/1000th or a millisecond. So that's interesting. It's a sound that's times that, so therefore, you know, some number of each of these is a millisecond, I guess, is what it's assuming. Interesting. Tau. Then you have a distance, 0. Then you got, is make vector index less than n1? Did we decide what n1 was yet? Number of data points in the acceleration phase. Okay. So yeah, there's some number of data points in the acceleration phase. So while we're in that area, we are doing something called dist, I assume distance or something along those lines. Fs, which again is a starting feed rate of a block. Okay, and it's only used here in this make vector, which is interesting. I just did a backward from the top and it came right here. So yep, it's that times our number of milliseconds times 100 or whatever, or yeah, some number of milliseconds plus a half times this XLP, which again, well, I'm going to do this. New view into file, something like that. Oh, they used to have that here. Split view, thank you. There we go. That's what we want. So yeah, XLP is our acceleration prime. That is, it's an acceleration value. And then we're squaring tau. Fascinating. So you have this times this, and we can just quickly do this just to get them isolated. And yeah, so that's fascinating. When you're multiplying by a square, starts to get, into the realm of angles. I'm starting to think about hypotenuses and angles and things. Meanwhile, yeah, again, you have your XLK is just your XLP. Then you got, are we in the coasting area? That's what this is about. And if we are, then we handle the coasting stuff. And in this case, we've got this S1E value, which has been calculated earlier as part of this whole load block data area thing. Plus your FP, which is your feed rate prime of the block, times, again, your tau, which is time, I assume, based on these, but again, a millisecond, I'm not entirely sure. But that's what they said. That's what they said, man. They said it was time step. So yeah, just calling it a time step. And I assume, again, this has to do with how fast you're moving, therefore reckoning it in milliseconds makes sense. Since we're not doing much beyond, we don't have like, 1 million moves per second or anything like that going on in Marlin. But thousands and tens of thousands, definitely possible. Meanwhile, you have this tau, which is the difference between the original and some difference. So yeah, you can see what's going on here. Tau equals the difference in time. And here you have, this is also a difference in time right here. Tau minus the amount of time spent coasting, or no, accelerating. So we're remove the acceleration from above. Again, here you have now remove the coasting from above, but not the acceleration, which is interesting. So this would seem to indicate that it's both the acceleration and decelerate. Oh, well, actually, it's coming in here when it could be accelerating, could be coasting, could be decelerating. So yeah, fascinating. So yeah, then you get your decel P, which again, acceleration prime of block. Hold on. In there. Oh, that's why. Oops. That should be easier to see. Okay. Okay, so yeah. What else we got? Well, we have the next thing that happens is XD in the make vector batch index. So we're making a vector, and this is a batch index. And so the XD of that is your start position plus your ratio times your distance. And that X ratio and start position all calculated externally, but the distance is not. I assume the start position is in this up here somewhere where the not where the block is being reset, but where the block is being loaded. Yep, sure enough, it is being set in the loading part. So that's cool. There's some fascinating stuff going on in the loading section, so we'll have a close look at that soon. But yeah, you've got your start position, x, plus the x ratio times the distance. So it's pretty fascinating what's going on here. Then we're doing the same for y and z. Next, if there's an extruder, we look at the linear advance. Yep, there can be linear advance inside here. And this is all being handled by this new code. It has its own linear advance, which is absolutely fine. But I would like to get our linear advance variables to apply. I think that would be cool. We then have so this is when we're in linear advance. In case you're curious, I may skip over the details because linear advance is a separate kind of subject. But in general, I see that it's doing some interesting things. You got your E ratio times dist, but then it's subtracting this raw Z1 or Z1, you prefer, which is related to the, yeah, it's clearly related to the linear advance elements. So we have this, yeah, start position plus E ratio times distance is already right here. And then it's subtracting that. And then it's giving an adjustment, which is multiplying by this Fs, which is, I believe, the reciprocal of the Ts. Yeah, so here it's, again, it's, if it has to be the 1 over fxd I control Ts, then we're going to not make those separate. We're going to join them into a single option. And then I'll make a, reciprocal or whatever. So you could say reciprocal Ts instead. And that'll be it'll be a constant, so not a big deal. And also we like to multiply, so reciprocals are good. Meanwhile, yeah, and if the E ratio happens to be greater than 0, then it's doing some, excuse me, it's also doing a little advance K stuff based on the acceleration. So that's interesting. And as we saw earlier, it is an acceleration millimeters per second value. So multiply the acceleration, as it were, by this advanced K value, which is, if I look at it, it is a configuration value. So it's our K value, basically, as you're familiar with. And I definitely need to look at that and see how it relates proportionately to the K values that our current linear advance uses. The default, and it doesn't say much about it. It's called linear advance gain. So if it's in the same units that our current linear advance is in, which it sort of seems to be, that will be nice. That will make me happy. So yeah. So here we have, the next thing that happens is it takes your ED, which is, again, it did XD, YD, ZD, so ED equals, same idea, E advanced plus det adjust times this, similar to these, but it's based on this. And again, start position is involved. The ratio is involved, the distance is involved, so they're all there already, but adjusted for advance. Then you get your E raw Z1, which is already this, which is interesting. Like, why would you, again, I feel like pre-calculating this stuff. So like you could do this, unless it's already there. Oh, it is. Can't modify it, sorry. So I could do something like const float, new raw Z1, Z1 equals, something like that. And then just, you know, oops. Something like that. Assuming none of these other things changed either. Let's see, E ratio, nope. And dist, nope. So yeah, I think that's safe. I'm sure the compiler's already handling it, but, and this again too, right? So in a case like this where it's assigned and then copied, I do wonder if it would automatically, like, I mean, it's just copying it. It's got it in a some kind of register, I assume, at this point. So I'm not too worried that's going to add overhead. But we can always find out. Do our profiling. ED. So alternatively, they have this going on here too, which is interesting. Equals E start dist plus extrusion divided by the sum of basically the total number of steps for the whole move, which is interesting. Were we right about N1? Yeah, number of data points in the acceleration phase, coasting phase, and deceleration. Yeah, so I may find better names for those than N1, N2, and N3, but they're simple enough. Generally speaking, we used to use NR for number of things, but that kind of fell out of favor because NR is just, it's weird. It doesn't translate well. Or it doesn't make my brain tingle in the right way. Meanwhile, so the next thing that happens is it takes it takes that and copies it into this, which is interesting. So you could conceivably, put that here. Or you could even do something along the lines of like, well, you're going to change it anyway, so why not do E advanced Z1 equals this instead? And then in that case, you're doing a plus equals and then you've already done it, so you don't need to do that. You could do that if you wanted to. Just to give a sense that this is actually being modified rather than, reassigned to a brand new value. It's actually gaining this adjustment value times your time interval, 0.001. It's interesting, times a millisecond, I should say. Again, I want to be careful about this. I want to make sure I understand when things are time versus other things. Unit delay of advanced extruder position. So yeah, it is actually a delay. So I'm going to put that down as MS, I guess. That makes sense? I may be completely wrong, but I'm going to watch how it's used and we'll see. Yeah, and that's the last place you find it. And it's being used, it's moving forward and constantly changing. When it's at reset? Well, it's reset at the end of reset, interestingly. That's good to know. And how we conceive of motion is always an interesting thing, too. And in terms of linear advance, I remember that the documentation always refers to signals, like the signals are staggered or the signals are, so it's like, yeah, I guess it's a signal officially, but it's also, causing something to shake. So it's quite a signal. Is that like the movie, The Signal? That young adult book adapted into a film. Has Z-axis, ZZ1. equals 0. So this one is maintained here, and it just is keeping track of its own little thing. So basically the last time it was calculated, the last time it was used, if the z value changed, right? Yeah. So this is actually, I believe that's a z coordinate then. ZD doesn't equal ZD Z1, or maybe it is time. We'll see. Next, you have, what's ZD again? Show me. ZD. Right. Fixed time trajectory and modified fixed time trajectory. So D is a trajectory. Oops, I did that again. Got to fix that. Okay, that's better. Fascinating. Yeah, so one of the ways I've been able to keep the synchronization between the bug fix and this branch is I just use git diff. And that seems to work. Remember that movie Being There? Shepherd? I like to watch. That character, he was sort of a symbolic shepherd of some kind. Being There, that was one of my dad's favorite movies, along with Little Big Man, which both of them grew on me over time. Meanwhile, right, so this is multiply by ZD and add yourself. Cool. So that's base frequency times dynamic frequency K times, and that's for your x-axis, I assume. Oops, here's a place where I need to don't do stuff for y. Oh wait, no, this is for z, right? So if you have z, then it assumes you have x and y. I haven't made it, I haven't set it up to do, you believe you saw that movie. Well, man, you're missing out if you don't know. Being There is one of the most amazing comedies, and but also, you know, social commentary movies of all time. Pretty awesome. So we've got this thing going on. And we also have this thing called mass-based frequency mode. That's kind of cool. We'll learn more about that over time, I'm sure. But yeah, so here we have our block being, we're making a vector. We're setting it up with, if we haven't followed through here, we're looking at where are we at? We're in the realm of acceleration, coasting, or deceleration. And I should be adding more commentary to this really as I go, because I need to make sense of it as much as anything. So we could say, deceleration, there we go. So just to keep that in mind, and we have our f underscore s, and then you have your s underscore, I feel like this should be s underscore f instead, just cause, but nope, oh wait, this is capital F. Oh, now you're confusing me. Well, anyway, the naming of this stuff is not the greatest, at least as far as my understanding, but starting feed rate. Meanwhile, you have this thing called f underscore, was it p? Oh, same for both. And that one's being calculated, and that's the feed rate prime. Oh, okay, cool. But I do want to make it lower. I just want to call it lowercase. I'm just crazy that way. I don't know why. Well, let's keep it capitalized for now. Don't want to confuse Ulendo. Yeah, Being There is great. What was the other one I mentioned? And const, just because. There's another movie that came to my mind recently. Of course, I'm watching the series The Last of Us, based on the video game. And the character Joel is really quite a stoic and interesting character, having gone through some trauma and lived 20 years through a zombie plague. But one of the things that he reminded me of was this character in a movie called Limbo, played by a character is also named Joe. I think it was, I remember his last name, Joe something. But he had gone through some trauma. He had been in a boating accident, and his friend died, and he had blamed himself. And he had lived for some decades or some time after that, and kind of just had to go and live a more obscure life. So, but as a character, he's really fascinating. He's like he's the kind of guy who would just like, he's in a situation where people are looking for comfort, but he won't say anything that's not true. So he's like, I'd like to say some comforting words, but right now, if we're going to survive, we need to acknowledge reality. So this is the situation. But yeah, it's a really fascinating story. Cool movie, Limbo. Check it out if you haven't seen it. David Strathairn, Mary Elizabeth Mastrantonio, and someone else whose name I can't remember, a young actress who I don't know if she ever went on to do much more, but really good performance by her. A very small movie, but a little microcosm. But it's got some action. So okay, what are we doing? Oh yeah, let's look at this here. We're into the next part. So yeah, we have our acceleration, deceleration, and we're figuring out what our accel k should be based on our accel key and our basically acceleration values. Clearly, there isn't any acceleration happening here. So yeah, that's basically the amount of speed we're adding per step is what accel k is about. Meanwhile, for E, it's taking that and it's doing some adjustments for your linear advance. All cool. And then you're getting some new start position plus ratio times distance, and the ratio being how much time has passed, essentially, since the last thing. So this is all being handled in a kind of like, if you've ever written code for or played around with a game engine, you have this like fixed time thing going on, but you also have like this, as often as possible thing going on. So with Unity, for example, you'll call a thing that's, only going to be called 30 or 60 times a second to do the frame update, or maybe once per frame, but you want to have things that happen at regular intervals. But then you have this time value, which is the time delta. And so if you don't necessarily know how much time has passed, you can look at the delta and say, oh, this much time has passed, and therefore this thing should have moved this far. And so everything's handled at that level. And this is similar in that way. It's like taking things and looking at how much time has passed and then giving you a proportionate move and a certain number of steps in that direction. And then if there's other moves to be done or direction changes or whatever, that's handled. And most likely, I would think it would chop off on block boundaries. But I don't know, that's kind of the way we've done it in Marlin up to now, using the Goebel approach. But with this fixed time approach, it's a little different. Meanwhile, here comes the shaping, if it's on. So if we're between 10 and 19, then we're in shaping mode. So you can actually enable this and use time-based motion, no shaping, and you just get time-based motion, presumably somewhat more regular. So you may see even a reduction of artifacts just from using this time-based motion. How much we want to retain this time-based motion as a formal part of Marlin is, I'm not sure yet. I want to see how that goes, but I feel like it's not what you would want to use on an AVR. You kind of have to go with this crazy motion system we have from Goebel for your slower AVRs. So we're going to keep this, keep the older motion. But if I can somehow mix the two, that would be pretty awesome. So yeah, here's your X, here's your Y. Doing the shaping. So shaping is very fascinating. So you can see here how much shaping is involved. Well, it's all done in this little block, it says right here. What does that mean? Well, okay, we'll look at it. First thing it'll do is it gets its XDZI, which is, looking it up, data point delay vector. Okay, whatever that is. Data point delay equals data point of the current batch index. Okay, then you got, now we're taking this and modifying it, and it is coming from XAI Z 0. Right, the first thing in the XAI, which is, again, checking this out, shaping gain vector, and there are 5 of those. First one is 0. And we're going to see that later on we got XY max I, and I believe that comes down to what type of, yeah, the vector length for the selected shaper. It's called a vector length. And as you can see, zooming down to the update shaping stuff, which we'll look at more closely soon, it's doing different things for different shapers. And you'll see that your simplest shaper, your ZV, has 2 parameters. ZVD has 3 parameters. TEI has 3 parameters plus some other fanciness that it applies to those. And here it's doing this little bit here where it's XAI equals XAI plus. I'm just going to do that times equals instead, because that always annoys me a little bit. I just like my C++ shorthand, my C shorthand. I'm a glutton for that stuff. So yeah, anyway, it's doing is it's multiplying each of these by some adjustment, which, oops, yep, already constified down there. So yeah, that's which is a reciprocal of sum. So that's interesting, of the sum of all of these values in the EI. Then you got this thing called 2EI, HEI, which gets even fancier. It squares this thing. Yeah, now you'd be glad to know these don't get called super often. So, and yeah, it figures out the vector values and all these, and yeah, then it also, as you can see, is the adjustment is the reciprocal of the sum of all of these, which I have a thing where if you take a reciprocal of 0, it just makes it 0, whereas here it'll give you not a number, or maybe infinity if you divide 1 by 0. So yeah, you have to be careful of that. Meanwhile, 3HEI gets even more parameters, and you can see they're scaled. There's a 0.625F times, you know, and if you take 1 over 0.625F, that gives you, what, 16? So yeah, so you could say, you know, 1.0F divided by 16.0F, you know. You wanted to get, just so you know what's going on. And here, of course, 1.0 F divided by 4.0 F. Gives you that, and you know, this here is divided by 2, of course. And this will all be pre-calculated, so it's just maybe convenient to be able to see it. I don't know. But yeah, fascinating. So the amount of square root and stuff going on here, it's all beyond. I mean, if we were to look at the mathematics of this and graph it out and stuff, it would start to make sense to us. There are actually good papers that cover this math and these techniques. So I don't need to get too into it. If you're very curious, go searching on input shaping and download some PDFs. I have a few that are fascinating to read. There's also a good paper on the filtered B-spline approach. So, you know, that's also pretty cool. Here, okay, so yeah, max I is just basically the size of your vectors. So it's going to be looping, and when it does this loop, it's taking the difference between this index and the previous thing, and from the ni thing, which is also based on update shaping n. So as long as we're looking at the A stuff, we might as well take a quick peek at the N stuff. When you're doing the N stuff, it's looking at your the past zeta value and your X factor and your Y factor. And then it's setting these up. So you get your X factors and your Y factors. And again, these are all just fairly simple. They're all, at least here, this one is that one is that. Simple, I guess. This one, and this one again, 1/2 divided by. I wonder if that can be done with multiplication. Guess not. I mean, 1 divided by something, it would be lovely if you could do like multiply and get the reciprocal of something. I know you can get a reciprocal by probably the floating point libraries are faster at doing reciprocals than regular old division. Don't quote me on that. I have a feeling there's an optimization there. I should look that up. I should know this by now. So here you've got xni and so on. But let's take a quick look and see what these are. Okay, they are int32s and they're time index vectors. Okay, time index vectors. So since they are, these are floats, but you're ending up with a uint32, there are probably ways I could maybe optimize this to do it all in integer math. We'll have to look into that. It'd be nice if you could optimize it a little bit. Again, this isn't called that often, so using float is probably just fine. You know, it's just a matter of how much one cares about the performance. And I like to save a few electrons when possible, maybe. But I suppose if you're using your 3D printer in your house and it's generating heat, then maybe you're saving a little on your heating bill. I don't know. Hard to say. During the summer, want to keep things as cool as possible, right? Meanwhile, yeah, so your ZVD and your EI both use 2, and your 2 HEIs are using 3, and you can see it's 2 times that, 3 times that. Interesting that this is, 2 times and not just the sum of, and this one being the sum of the previous. I assume that when this gets optimized by the compiler, it's just, using addition instead of multiplication. But we can look at that, we could see. I wouldn't mind if it was doing a little addition instead of multiplication. But yeah, the idea there would be obviously that. So you're just taking that one, and then you're taking the previous one, and you're getting what you want. But we'll see. Maybe that's an optimization, and maybe the compiler is smart enough to do that. Although you have cases where maybe they assume you're doing scientific engineering and you really want to evaluate how well the floating point or the integer multiplication, I should say, works, and you want to definitely use multiplication just because, I suppose. But I would guess that the compiler is going to do the right thing here. So yeah, you get these, and the other thing that's interesting about this is that if this rounds, then that means that each of these is based on that rounded value. And so you could be losing a teensy bit of precision in the 2, 3, and 4 elements here if you care about that. So I don't know. Meanwhile, and the default is, I guess, they're all 0. It just sets them to 0, which was interesting. So, yeah. So that'll actually happen during a init. Coincidentally, it'll happen during the init that gets called from the loop when it's not initted yet. Fascinating. All right, so here you have the shaping actually happening. And what's fascinating about this is all it's doing is it's doing a little loop and creating a new z-diff, and I assume this is changing over time. Or, well, I see, we just need this value. I'm probably just using pre-calculation here so I can read it more easily. But yeah, you can see each time it's taking that, it's adding to the XD the distance, I assume, that it wants to move times the shaping stuff, and then it's fascinating. So what's interesting about this to me is that it's breaking it up in such a way that it's like I'm figuring out how many steps, I guess, basically, or the distance for each of the shaped bits. And where does the timing come in is the interesting part too. Is I guess it's using the difference in time based on the factor, the shaping factor, or the frequency, basically, value that's been extrapolated out into these little arrays. So that's pretty fascinating. Right? Yeah, pretty fascinating stuff. So we begin to see hints and clues about how shaping works in this instance. But essentially, it seems to be doing it by splitting up the lines into smaller groups and then carefully timing those little groups, which is pretty cool. The way we've done it in Marlin was really like every step. It's like doing a corresponding anti-step later in time. Well, I've also think of, like, gaming PCs are little heaters too, right? So yes, your heated chamber could be your whole house, really. Then you want to get the liquid cooling and put it all over your walls. A little liquid cooling chamber. But then you have to deal with the aquarium like motor going all the time. My favorite cooling of all time is like the cooling that's used on rocket engines. That to me is the most fascinating. You've got these tubes on the outside that are running pressurized, basically fuel through these little tubes and keeping it cold. And it can't ignite because it's not able to mix with the oxygen, so it just stays cold, and it's just fascinating. And so that way your rocket engines don't melt. Because they're right on the verge of melt. I mean, they would definitely melt if they didn't have that cooling wrapped around them. You have to cool the room in the winter. That's amazing. That's crazy. I'm thinking you should just take that air conditioner and then stick your PC inside the window air conditioner and combine them, and then just keep your PC in the window. And then during the summer, or you can use it for cooling, and then during the winter, you can use it for heating. Just run like a very slow breeze through it in the wintertime. I'm sure somebody has done this. Oh, condensation. Well, that's the thing, is you need to have a condenser that catches it all before it gets to the PC. Although at that point, then you're kind of like, yeah, your heat exchange has already happened at that point. But I mean, I imagine as long as your temperature is like in the, below 35 degrees Celsius in the, in the lower, you could probably still capture and remove some of that heat. And it also depends on materials and stuff, which is, again, fascinating stuff, right? like the idea of a piezo generator and being able to, or a Peltier, I should say, sorry, like a Peltier cooler, Peltier heater situation. Those things are fascinating. So what else happens after this shaping? So pretty fascinating. It's doing the shaping magically on X and Y right here before our very eyes. It's setting up the XD of your vectors and giving you basically a set of timings, I guess, essentially, for the steps to occur. And as you can see, it's adding to each one based on your udiff x, or this is actually interesting here. This is just, right here is, this is just circular buffer crap here. It takes in, like, if udiff x is negative, it needs to wrap it around, basically. So, yeah. You could probably simplify this by using a proper circular buffer in some sense, but for now, I'm not touching it. It's too scary. Until I know it better. And then you have this kind of thing. Call me a traditionalist, but I like to combine these things. And this costs nothing to say greater than or equal. But in general, as long as you know you're only incrementing once and you're not too worried about cosmic rays, that should work fine. And again, cosmic rays, they can be bad either way. So let it be. So this is, you have if, and again, same idea. Advance the make vector batch index, and if it has reached the end of the make vector area, and you notice, yeah, we've got this 2 times. So why twice, you might wonder? Well, that's the magic of input shaping. You've got 1 timing, and then you have some future timing. And even though the shapers are set up with like 4 vectors and whatever, you still end up with like this, you know, you may have irregular advance step, or I should say shaping steps happening, but they're all, you know, it's definitely doubling up. You've got one and you've got a later one. And maybe that later one is based on, you know, a very simple ZV timing, or maybe it's based on a set of resonances. But either way, you still get what you get. And that fascinates me. So what I see here happening is that it is, basically it's spacing these things out in such a way that they are shapeified, which is really cool. So I'm beginning to kind of grok what's going on here. Meanwhile, if you've gotten to the end, then your batch is ready. So it's basically, it wants to fill up the batch. That makes sense. Here we have, if we've reached max intervals, so this thing is getting advanced after the fact, then we can reset it. And we're also saying the block procedure is done and the block procedure is ready as well. Or not ready, I should say. Block proc ready, no. Block proc done, yes. And then we reset to 0. Simple enough. And just in case you were wondering, it's an unsigned 0. Just gonna drop that. I'm funny that way. I think I can probably get away with unsigned 0s in all cases. If it complains and says, hey, what are you doing, man? Why are you setting it to 0? I can't tell if you mean signed or unsigned, man. You got to be clearer. If the compiler complains, I'll change it back. Okay, so anyway, yeah, it's all beginning to fall into place. In a way, I feel kind of ashamed, because if I really studied this hard, like at some point in the past, and studied other shaper code, I probably could have done this myself. Maybe in a totally different way. And who knows? Maybe in a better, worse, terrible. I don't know. We'll see. My style is generally try to be simple, but also I like ternaries. So it's sometimes I like simple, sometimes I like ternaries. All depends on my mood that day. So this is pretty cool. Let's make some notes. Filled up the queue with shapy steps. I guess I shouldn't say shapy. I think it's steps. We'll need to say with shaped stuff. So we start again at the batch size. So this makes sense. So you have a batch of stuff and it's getting thrown into a buffer. Boom. And then, oh, hey, Alex Gibson, what's up? Yeah, have a good rest. And this will be waiting. I guess I'm keeping these things posted, even though sometimes they're a little awkward. I'll keep them up. I'll definitely go back through and make sure I don't say any stupid things that get me canceled. But otherwise, yeah, you'll always find my old live streams hanging around. And I might even put some captions on them if the AI does a terrible job in the future. But I do like to also break them up by section if possible. So this one's got a lot of topics, so I'm going to be breaking it up by section for sure and putting little chapter markers on there. This chapter marker will be me describing chapter markers. So yeah, when it's reached the shape stuff, so then we start at that's cool. So you have a batch, you fill it up, and then the second half is, boom, the shaped bits. And those shaped bits, I guess, always come later. Because we're assuming that, like if you're talking about like 40 milliseconds a lot of these times, like your machine is swinging back and forth at, these frequencies are pretty low, surprisingly low. They're sometimes even audible. I mean, 40 hertz is, in the realm of audible, for sure. So fascinating stuff. So yeah, batch is ready. Gotcha. Filled up the queue with regular and shaped steps. Yeah, I was going to say shapy. Some people use shapy to mean naked. I had a girlfriend who liked to say shapy. I'm all shapy. Miss you, Molly. How are things? Anyway, we have this bit, and so now we've reached the end of our vector index. So this is kind of fascinating. So we have a shape, we have a little bit of bitty vector, and then we have a shaped set of bits within that vector, I guess. Let's look at the make vector index part and see where it's used. Okay, so yeah, if we're in the make vector area, then we're going to be talking make vector. So yeah, is that what we've been looking at? We have been. Okay, so sure enough. So now we'll get a little bit of insight here. So we're starting out with, we don't know what our acceleration is going to be yet. I see here that it's been set to 0 already, so that's redundant. I'm just going to make a note of that. If this were a static, that would be one thing. We're using the stack for this, though. So, or maybe even a register of some kind, who knows. Meanwhile, so yeah, we have, we're making a vector. That's all I know so far, is what is a bloody vector. All I know is, so far I haven't seen it used as an index in an array, but I bet it is somewhere, right? Right? Sure, somewhere? I'm not seeing it used as an index in an array. I get the sense it's more of a counter than an index. But, people with insights into shaping in general can tell me what they think. So anyway, so we have a batch index, that makes sense. Within the vector, you have a batch. And then I'm feeling like this is like Max intervals. Okay, what is intervals again? Max intervals again? Total number of data points that will be generated from the block. Okay, let's look at how it's set. Acceleration plus coasting plus deceleration minus 1. So max intervals is interesting. It's actually 1 less than the total number of, I guess, steps again. What is N1? Was it steps or was it, it was data points. Okay, we're just going to call it data points, okay? For the time being, we're going to call them data points. So yeah, we've got max intervals is accel, coasting, and decel data points. And we'll just say 1 less than the we'll just do this. Good to know. So that's basically whatever data points means. We're going to find more out about data points soon. 1 divided by 2 times. Sometimes we've done 0.5 divided by the thing instead, but it's called 1 by 2a, so what the heck. Again, it's just reciprocal. Again, if we're going to be doing a division anyway, then a multiplication is, you know, only adding more. But I am going to presume that if I look at the compiler output of this, it's just going to be 0.5. But when it comes to floats, compilers can be very stingy. I remember there's one thing where if you say multiply times 1.0, it'll actually leave that code in, unless you set a flag on the compiler not to. And if you set the compiler on the flag not to compile, you know, to compile it to, you know, optimize times 1.0f, remember it introduced bugs in all the other places, so I couldn't use it. So it's like it all depends on what version of GCC you happen to be using or whatever. So yeah, that was on my, I was getting on my nerves a little bit. Anyway, let's go through and do a little bit on this N1 stuff. So here we have, this is, yeah, I want to say acceleration, again, data points times milliseconds. I'm not quite sure why it presumes a millisecond, but yeah, time step for trajectory generation. So I guess it's I'm going to call it resolution. I don't know, using underscores kind of does give you the sense that it's like, you're going to have to search for that thing. And I'm even going to use an X instead of a star. How about that? Screw them asterisks. Then you have your coasting. Data points, and of course your deceleration. So again, we have, these are some kind of time. You know, again, presuming that it's a millisecond is interesting. I don't know what that means precisely. So now, yeah, I'm going to get together with these guys real soon, talk about this and figure out. The Ulendo has been really cool about, you know, meeting up and giving time to discuss this stuff. Given my weird schedule, it's like I'm lucky to catch them at all sometimes. Here we have this down here. You'll see there's a square root of 2 involved. 1.41423. Oh my God. I'm sure we don't have that many digits, especially for a float. But what the heck? Can't hurt. Although I think I do have something like called square root 2 somewhere. I feel like it's defined, but I guess not. Yeah, I thought we had it, but oh, whatever. It's just so commonly used in all kinds of code that usually it's defined somewhere. All right, so then we have these N1s. All right, so N1 is, again, this is interesting because it's going from T, which I presume is some kind of time unit, to data points. So again, we're going to say data points. And this is based on FS. So that's interesting because what? This is interesting. From time? Yeah, we're getting into the weeds here. I notice I am going like backwards. Sometimes that's the best way to work, I find. It's like reverse engineering. That's why they call it reverse engineering, people. Data points from time. So here we have something called N1, N2, N3. And clearly these are data points based on time. We are also rounding up, which is a good idea, because you want to make sure you have enough time. And also, if you have a certain amount of time, you might definitely need that extra data point. So even a tiny slice of time might require that extra data point. So, and again, this is Excel data points. I suppose. Here, we'll make them all the same length. Excel coast decel. But that. Rounding up. All right. Now what's interesting again here is that now we're getting these floats, which is taking this and multiplying it by this. So I guess that's because these don't have to be reciprocals of each other. If this were 2,000, these would be twice as large. Thus, this time would also be twice as large. It's fascinating. So again, what does that represent? That 1,000. It's interesting too that it is an advanced. It's kept as an advanced property, which makes sense. Yeah, this one. FS, frequency for trajectory generation, 1,000. Oh, and also frequency for stepper IO update. Ah. Well, that's interesting. That's 20 seconds though, I assume. I want to say seconds here. And 1/seconds, which I guess is already marked, but actually not seconds, it's 1/seconds. I don't know what else you call that. Duration? I don't know. I mean, it is not in seconds. Hertz? That makes sense. That's what Hertz is, right? 1/s. And this is again also Hertz, I assume. Or no, maybe it's milliseconds. Or maybe it's Hertz. I mean, I guess it's the same thing in a sense. 1,000 Hertz, do that. Also, I like to do this. All right, getting really, really nerdy here. Hold on. Oh yeah, I might as well do that too. Got the space for it. Oh. Yeah, I think I need to go one further so I can line up with that 10. All right. This one's fascinating. Ticks, minimum stepper ticks between steps. Now, if it's always going to be stepper timer rate divided by something like this, then that makes sense and we can probably do that. I would say the best thing to do here would be use that as the base value and then change this so that it's actually a modifier. Instead of min ticks, it would be tick adjust or something like that, ticks ADJ, and then you would have 0. And then if you wanted to mess with it, you could add 0, 1, 100 or whatever you need to give more time or provide less. I don't know if you'd ever want to do less time. I suppose you could, but that's pretty fascinating. So it's stepper timer rate. So if you had a stepper timer rate of, oh gosh, let's look at what stepper timer rate actually is. Stepper timer rate is based on the HAL. And it's a timer that is like, can conceivably run faster. I think the way we ended up doing it was the stepper timer runs at a regular frequency, but we use, to get the intervals, we use a counter ceiling, a top value. And so it gets less and less accurate the lower that value gets, or so the faster you go, the less accurate it becomes. It's kind of like when you have like a situation with a game engine and you've got 60 frames per second, but as soon as you get a little extra overhead, suddenly it drops immediately to 30 seconds, or 30 frames a second, because every frame is taking just a little bit longer, and so it has to wait that whole extra frame before it can do the update. Which is why we like 240 frames per second in our games now. Because if you do get a hiccup, it's not as noticeable. It's still noticeable once you get used to it, but yeah. You gotta use a screen that has like a low latency, and then there we go, or high latency, I should say. So yeah, these are gonna change, I imagine. I do want to change these. So anyway, back to this code. So I'm beginning to kind of get a sense. We have these, and these could be different from each other. So very good. And I need to know what this really means again. What does it really mean? Again, it's, oops. Hit the option key there. Yeah, so again, it's 1,000 frequency for trajectory generation. Okay, well, I'm just going to make a note of that. Based on frequency. Based on frequency. Yeah. Okay. Then you got T1 and T3. T2 is all done above. But what is T1? All right, so f of n. Current block's nominal speed. Okay, good to know. And it also changes if T2 changes, so we need to know something about that. But I notice, I don't know if this is modified. It doesn't look like it is. I'm actually going to move this down a little to here, where it actually gets used. because this is where it's assigned and modified, but never afterward. So it just seems a little more logical to put it there. Unless it was meant to be up here so you could start thinking about it. I don't know. I'm reading the code and I need to think about this, man. All right, so we have, oh, I also did this little SPM thing earlier, so it's me. Okay, so you have the current block's nominal speed. That would be how fast do you want this block to go, if possible. And that's, and nominal speed is in units of millimeters per second, right? Just to remind ourselves, millimeters, per second. And that is not steps per second. Last I checked. Maybe it is though. No, it's millimeters per second, sure enough. And it is a float. Okay. Okay. Yeah. One of these days, maybe a fixed point planner will suddenly appear. Those old AVRs will just scream, and I don't know if we'll be able to do any kind of shaping, but we might be able to. Integers are fun. Fixed point's fun. You can represent all kinds of numbers in fixed point. It's great. Okay, so here we've got a nominal speed, gives us our frequency, millimeters per second. Now we're taking the reciprocal of that. That would be, instead of millimeters per second, it's number of seconds per millimeter. Like that. How long does it take to move a millimeter? Yep, times the total length, right? And then we're subtracting. So we're figuring out the time it takes to move this amount. So everything from here being multiplied is some kind of distance, essentially. Not just distance, possibly, since it does involve time, it may just be that it's involving, extra time that's required for certain things to happen. So yeah, we'll see. So if it happens to be less than 0, which this is an optimization we could possibly get if it's never less than 0, but it does subtract from the total length this whole bunch of crap. So yeah. You could do this kind of thing. Minus this, plus this. But that's stupid. We really want to understand what these are in terms of their differences and stuff. Okay, so if it's less than 0, then if we can't reach the, so that's interesting. It says it can't reach the speed. So it looks for an intersection. I would think you could maybe do half or something, but we'll see what it's doing. So instead of that, it's taking the square root of the total length minus these things, dividing these things. So is any of this borrowable? Let's see, one thing is borrowable is I could do a temporary value for that. FE, FS. I assume that's start minus end. So we'll just say squared by 2, and it's A to B, or it's N to start, and it's DA, and it's also interesting. There's an E and an S and a D and an A. Well, I'm just going to call it FDiff equals this. Right? Yeah. And I'm just going to use that. Again, the compiler will do this for us. It's not like I really have to do this. It's just for my own. I want to take these little bytes and I want to understand them on their own. So 1 by 2a, 1 by 2d. Yeah, and here we have a sort of an O-diff, I guess I'll call it for the moment. Since they start with O, right? So let me see what's going on here. Oh, I guess we could actually do this. Move that here. Yeah, it commutes. And then we can get that diff. Right? So that clears it up a little. Clip by intersection if speed can't be reached. Now we're using, square root. Fine. I would like to avoid using square root, but it is in the user thread, so at least there's a possibility that we'll be using an FPU. I assume. Definitely check. I'm going to mark things that are called from interrupt context, like sooner or later. Maybe now. Anything that might be called from interrupt context is, yeah, so this is actually called from the non-ISR task. Good. Great. I'm going to figure out a name for that. Should I call it just userland code? Userland? I live in userland. So yeah, so that's pretty cool. So clip by intersection if speed cannot be reached. And T2, I assume, is, yeah, no coasting, basically. So, okay, this is telling us that it's accelerating, but it hasn't reached the top speed yet. That's good to know. Let's go with coasting speed. Or I should, nominal speed would be better. Because it is possible that you could accelerate and never reach it, and then you're already having to decelerate before you ever reach it. If your move is too short, you'll get acceleration just up to the speed it can reach and then back down. And also you have jerk as well, so you have to consider that. Although I don't know how much jerk is considered in all this stuff. I kind of think we already have our trapezoids set up. This is really going, and it feels to me like this is doing, well, it is doing some stuff. We got the blocks are set up, so they're already trapezoidified. We do have our nominal speed in there. Our milliliters are in there. Let's see where total length comes into play too. Wow. So that's interesting. It is a static, which, means it's always going to be in RAM. And it doesn't have to be. Could just be local here, because it's the only place it's used is in this one method. Also, since we already have it stored in RAM from here, we wouldn't necessarily need it. Also, notice that that's current block millimeter. I just feel like, I feel like it should be there. right? Yeah. Some of these things may be in the block. I don't think so, but like millimeters divided by step event count. This is, of course, you know, total length, yeah, for each step. Oops. And yeah, that's actually a float. Clearly, you need to float for that because the distance could be, we need very accurate value here. And even a double could help in some, possibly in some instances, although I figure we're close enough. The kind of error you'd get is like in the, you know, picometers, probably. But that might matter if you're doing like, you know, some kind of medical application with Marlin. So consider that. All right, so I'm going to just put the SPM in front of these. Just because easier to see. Okay, so you got your FS, and that's actually needed later. In other places, it's used in load block data and elsewhere. So yeah, we are kind of stuck with FFS being RAM-based. So we have steps per millimeter times the initial rate. In other words, steps per millimeter, so rate in terms of steps. In steps per second. Or is it steps per millimeter times rate? And that's actually the speed, not the acceleration. So initial feed rate, I guess I'll say. Initial feed rate, steps per second. And yeah, final rate in steps per second. We'll say with start and end, since that's how it's kind of labeled in steps per second. Now we've got good old acceleration. I guess it's being modified. Forgive me for doing this. Uh-huh. Interesting. Oh yeah, it is down here. It is actually being divided by the negative of A, which is interesting. So T3 is going to be negative? Or is it n minus that divided by, you know, you could just do this. If you need it to be negative, I mean, you could do this. You could say, instead, if you could say f of n minus f of v divided by A, and that'll give you the same result, assuming you didn't modify A, which you didn't. And, you know, this could also be minus 1 divided by A instead, or divided by minus 2 times A, if you preferred. You'd still get the same basic maths, I guess. Like here again, but then I guess you could say, oh, it's not 1 over, it's, yeah. So yeah, you could do a little optimization there that way, I suppose. That's the only optimization I could see. And then you don't need D to be negative A. You've already got that. I guess this would be, this is going to do a little extra, you know. But on the other hand, since that was that, it's just simply negative 1 by 2A. Right? Unless I'm mistaken, 1 divided by negative something, and like multiplying 1 by it times negative something. So just move those about. So this is interesting. Square times 1 by 2a. So what's interesting to me here is, well, I'm not going to assume, but I guess acceleration and deceleration distances would assume to be the same. We've never set it up where you have the ability to set a different deceleration value from acceleration. And there's some practical reasons for that. You know, it's kind of assumed that the machine's tolerances are the same whether it's accelerating or decelerating. But you can imagine maybe some cases where that could be tweaked. So you can tell me in the comments and future viewers of this video whether what I just did was just terrible. If it clears things up in some sense. But also, again, I'm pretty sure that your compiler is going to do the right thing, you know? And again, here we have this divided by a stuff, right? So here it would be nice to say, you know, const float, you know, 1 by a. Equals 1 over a. You do 1 division, 2 multiplications instead of 2 divisions. Now, someone tell me, is 2 divisions, 2 multiplications and a division slower than 2 divisions? Hard to say. Anyway, any amount of, you know, optimization here is good. In general, I don't know if this is marked volatile or if the blocks are marked volatile, but that's one reason to copy this, you know. Copy non-volatile volatile tile. Whoa. There. Is current block like, did I make it volatile? Hmm? Well, I guess it's being passed, isn't it? So, Well, anyway. Hey, good to see you, Shepard. Take care. Thanks for dropping by the Discord. And we have T1, T3. We've got that. Okay, so let's just at least put these down in what units they are, so we know. Difference in feed rate, so that's basically rate divided by your A, which is your acceleration. Over acceleration equals time. And I do believe we're looking at seconds here, basically. Okay. Fascinating. So you got your, of course, millimeters per second. And these things are interesting. Let's take a quick peek at these. So you have your yeah, I kind of see why there was a separate D. Like if you really wanted to have a separate acceleration, take a look at Planner real quick. T. So we have this thing called block T, and it has a thing called acceleration. Where is it? Oh, there it is. Yawn. And it doesn't have deceleration. How interesting. That's because... Now, what's interesting too is that a block can contain a complete move with acceleration, coasting, and deceleration. But when we're doing a lot of, when we do our, whenever we do our motion, or things like delta, or if you're using bed leveling with, small segments or anything like that, or you're doing curves, you name it, and in a lot of prints, you got a lot of smaller segments being made, and so you have a lot of cases where it's just accelerating and never decelerating, or just decelerating and never accelerating, or never reaches coasting, and yeah, so. But of course, the more quickly you can accelerate, closer you can get to those peaks. And the curvier we make those accelerations, it does tend, depending on how you curve it, you do curves like this, basically S-shaped curves, where it accelerates slowly, but then, once it's built up a bit of momentum, that momentum carries forward and, gives a little overshoot, and you can use that overshoot to augment your acceleration. There may be ways to that's kind of part of jerk too, is it gives you that little kick but jerk is instantaneous, and that's kind of fascinating. And we have a welcome a visitor from DIY3D.in. It's here. And you were looking for some kind of something recently, weren't you? Remember you sent me an inquiry about something. I have to look it up. Was it on Fostodon or someplace? Anyway, we have these, which are your squared. So why squaring? Why not square? Squaring in math is always a mysterious thing. So acceleration and deceleration are the same, so might as well go with or deceleration. Magnitude, should I call it? Then you have your 1 over 2 times y. Well, let's see, if you go accelerate and you multiply by 2, that would give you, how much did you accelerate in twice as much time? Then you divide by that, 1 over that, and that gives you, let's see, the actual speed that you will reach, I assume, in twice as much time. Is that right? Time reachable in should say speed reachable in at double accel. 1 over twice the acceleration. I think twice the acceleration. Acceleration is in millimeters per second per second. And the actual speed reached. Yeah, I'm thinking speed change in 2 units of time, something like that. And same goes with this, speed change, 2 units of deceleration, and you'll notice that it is negative. Good. Meanwhile, it's also squaring starting feed rate. Okay. Squaring the feed rate and then multiplying by that reciprocal, which is your acceleration essentially, or double the acceleration. Right. And here, you kind of get the same idea. You never have to really do this. Now it's interesting. Wait a minute. ODiff is 1 by 2a minus 1 by 2d. Well, the one is just negative of the other. And so if you subtract one from the other, you should always have 0. Am I missing something? I did something terrible, didn't I? One of the things is, of course, if it's not always the reciprocal, then yeah, you would have a difference. But, and again, why do you want to divide by 0? Can't divide by 0. Bad. So, oh wait, if it's negative, then that's actually just adding, doubling itself. So effectively doubled. Right? Which is what you want. Now what's interesting is, yeah, if you divide 1 divided by 2 times a thing, then you're basically, twice that would be 1 divided by just the thing. So you could kind of do this 1 divided by the thing and then divide that again by 2. Get that? I don't know. Do as little math as possible if I can. In any case, this gives us squared by 2a. So it's interesting to me that the squaring happens. I want to know kind of something about what that means. Like if you're taking a feed rate, okay, which is millimeters per second, and you're squaring it, what is that effectively doing? Millimeters per second times millimeters per second. Well, not entirely sure, but it has to do with, I assume, since we're taking a square root here and other things, that we're basically looking at some kind of angular change. I don't know. Here. Square of that. This kind of reminds me of like sine cosine stuff where you have weird ratios, and as long as you get those ratios, they'll turn out like you're similar to your sine cosine values. But they're not too explicit here about what they really represent. Interesting. Well, we'll get some of this sorted out. So starting feed rate squared. Time, basically divided by twice the acceleration. Gotcha. Divided by double the acceleration. True. Graphing this kind of stuff is fun. I'm really more just trying to understand the meaning, but I mean, graphing could definitely give a picture of what that means. And again, double the Excel, but also, you know, interestingly, being negative. So again, I think we're looking at a change. This is meant to effectively represent some kind of change in acceleration or deceleration. So, and then the diff. And then I see we've got a length going on here too. So I get a sense that what this really means is millimeters per second squared gives you some sense of how much time something's going to take or how much length distance you'll cover. And the fact that, you know, it is changing over time is like, yeah, you don't want to have to go through a loop and just keep like adding to the thing that you're adding and then having a running sum. So the squaring is, I guess, probably, I'm guessing, a quick way to accomplish the same thing without having to do any kind of looping. I know experienced coders are watching me going, you're so naive. You're so naive, man. Don't you know? It's first year code 101 stuff, man. Motion systems 101. Sorry, I skipped motion systems 101. I really need to go back. So anyway, we have this, which is, I assume, I feel like this must be the coasting distance in some sense. F-diff is the coasting distance. L-diff is going to give us the acceleration versus deceleration distance. Here we have 1 over f of n, which is nominal speed, millimeters per second. So yeah, I'm just trying to get down to the meaning of this based on that. So we have, in the case of millimeters per second, 1 over that is the number of seconds to go 1 millimeter. Times a distance, so it's basically time for duration, I should say. Duration of I see. Coasting. Or I should say, I don't know, nominal speed after nominal speed reached. Okay. If this was all pre-commented and I wasn't doing the commenting myself, I would probably still be struggling. How did they get that? Okay, at least now this week we could see kind of how it all gets derived and what these meanings really are. it can be tricky to know these things. But once you familiarize yourself with this stuff, it kind of like you start to recognize, oh yeah, that's the distance. Oh yeah, that's the duration. Oh yeah. So yeah, we're sort of working it out, but it's interesting that I'm counting 2 units of acceleration and 2 units of deceleration here. I'm not sure why the 2 times. Well, 1 divided by twice is kind of like half, really, in a way. So it's half of the speed change. I could say 1 divided by a, then divide the whole thing by 2. So I could say half of the speed change achievable. Interesting, though. You do need to know the starting feed rate. I'm also thinking in terms of like when you raise something to the power, like for example, the 12th root of 2. If you raise, hey, Lulak is here. What's going on? I was wondering who said that TI calculator thing. Yeah, so this is interesting is that when you raise the 12th root of 2 to the power, to the 12th power, you get 2. So as you're going along, you raise it to the 2nd power, square it to get the next frequency or whatever. Raise it to the 3rd power to get the next frequency, and so on. And they proportionately change, but when you get to 12, you get exactly that, 2 you started with, double. So that's how you get octaves, is you multiply, or how you get all the notes in between, one note and its octave is you multiply by the 12th root of 2, and that's the frequency you use. However, that won't necessarily be well tempered, so you have to make tweaks to those frequencies to get them to sound better together. You also have, with physical instruments, you end up with all these harmonics. And even with your ear, you can end up with harmonics. A human voice, can create weird harmonics too. I wasn't sure if Alex from UK would have gotten the reference. You never know. People have the weirdest obscure stuff, like, they'll go onto a quiz show and totally wipe the floor with all those scientists who didn't know anything about music. They seemed so bright until they got there on the quiz show. All right, so here we have this difference here. So what did I decide these were? Start rate squared divided by double the acceleration. So yeah, again, I'm thinking like, if you take the square root of something and you square it, you get the thing that you started with. So it could be that, these accelerations are sort of like when you're saying millimeters per second, you're kind of taking a square root in a sense. Because you're dividing by second times second, you could say second squared. I know it's not necessarily seconds squared, but it's, as you accelerate per unit, it's like it's constantly going up. But that's the thing, is we're using linear accelerations here. And so this is still, again, this is all very much based on a linear acceleration. We do have S-curve, and that's where things get really tricky. And we actually can mix S-curve with our current ZV implementation, which is fascinating because it just simply times it out. That extra pulse is timed out. We could conceivably do the same thing here, I do feel like. We just need to use essentially like a callback or a lambda or something for our acceleration and just let it, inline as much as it can. And hopefully we get a nice curve out of it eventually, but again, the more I study this, the more maybe I'll be able to do those things. So continuing that study, we have, so this is nominal speed. speed we hope to reach, hope to achieve, but not guaranteed. If possible, as usual, nominal speed. We then take this here, right? So what's all that about? Start rate squared divided by double the acceleration, or multiplied by half of the speed change. Should be using like speed change for 2 units of acceleration is, let's see, if you start out with millimeters per second and divide it, it's seconds per acceleration unit? Like that? So a reciprocal of that would be seconds per unit of acceleration. Yeah? Whatever that means. Yeah, these are definitely like, some of these things are like unitless. They have no unit per se. So you have difference in the time. We don't really know at this point. Start rate squared divided by double the accel. And again, end rate squared divided by double the decel. So we do have a negative number here. Which is interesting. So if this is a negative number, subtracting it, then we get a we should have a larger negative number here, I believe. And it's only used here. But fdiff has got to be, well, it's d minus a, so it's going to be a negative number minus a positive number gives us a negative number. Fortunately, I can do things like this. Take a peek and just see how much did I really mess this up. Let's take a look. Just so I know. Yep, same as it was. And you have your right. Relative. Well, change is relative, isn't it? For 2 units of acceleration or deceleration, or is it half of change for half of the acceleration? Damn it. Start rate squared divided by the accel. All right, well, I'm not going to worry too much about it. Let's move on. So assuming we have this is like coasting length, right? And if it's less than 0, so we should have if we have a negative number here. That's interesting. I'm assuming this is like the coasting, something related to coasting. And it is well, let's see, if you had the starting feed rate and you multiplied it by your acceleration, and then multiplied it again, it's fascinating. Fascinating and frustrating because I want to be able to picture it in my head, you know. But I need to write all this down and, you know, graph it, as you say. I wonder if I have a graphing calculator. Oh, I have a thing called Grapher, but I haven't played with it too much. I try, you know. New graph. Give me a, oh, I don't know. Default. So yeah, you could definitely graph these out, for example. So let's say we have total length, for example, be our starting value, and x will be, I don't know, x can be length and position. We can use it for both of those if we want. I don't know, it gets pretty fancy. I would love it. I mean, yeah, it would be really cool if you could definitely take if you could take a piece of code like this and feed it into an AI of some kind and have it spit out a graph and tell you what's going on dynamically. You know, just give you a bunch of sliders for the inputs. That'd be nice. That's the kind of thing I could see ChatGPT being good for at some point. I also do have a Copilot for free from GitHub. They were kind enough to set me up. I'm not limited to 60 hours like you are. But if you have a good project, you can get free. If you have an active GitHub project, or maybe you're getting good sponsorship or whatever. Yeah, you can get Copilot for free. I don't use it nearly enough, but it's really amazing what it can do. I don't know if you've seen me play with it before. This Copilot is great. If I just pull up this file, for example, yep, fixed time control, and I go to like, you know, 500 or whatever. Maybe it can tell me what's going on down here. Like, Copilot, help. Activate, enable globally. Start rate squared divided by double the Excel. Well, yeah. Let's try doing that without giving it hints. Millimeters per second change for 2 units of acceleration. That is to say, square of the start speed divided by 2. Yeah, that's true. But maybe it can tell me what the units are. This gives us units of, does it? Millimeters per second squared? One of the words, acceleration. feel like it's the thing about Copilot is it doesn't necessarily have insight into what you're doing. It just tries to imitate. And so in its emulation of what it thinks the right words should be or whatever, it doesn't always quite know what's going on. But if I were to try and sort it out, anyway, let's just mark it out. We'll figure it out ourselves. So here we have change in speed for 2 units of acceleration is, yeah. Reciprocal, yeah. I want to say 2 seconds of acceleration. Let's see, multiply 2 times the acceleration. Yeah, you would basically, that's how much acceleration you would get in 2 seconds. And then you are taking that and multiplying it by the initial rate, and the final rate gets multiplied by the deceleration, which is interesting. Distance if nominal speed is reached. Is that what it means? Maybe? Right. Change in speed for 1 second of acceleration. Really? Are you sure about that? If 1 by 2a is that, yeah, clearly it's not. It's a change in speed of some kind, though. Well, yeah, I guess it does amount to that if it's multiplied that by 2, isn't it? As it happens. Distance to travel if nominal speed is reached. Is LDiff equals total length minus FDiff. I feel like at this point you could be like, well, okay, LDiff is negative, then or like this has to be, one of these two has to be 0 for this to come out 0. This can't be 0 because if it were, you'd get basically infinity. So something here has to amount to 0, and therefore, but it's less than 0 is actually what's going on. So that could be negative, or this could be negative, but one of the two has to be positive because we're using a multiplication here. Either this is going to be positive or this is going to be positive. So fascinating. Meanwhile, there's our square f of n, which I think is what, nominal feed rate? Yeah, nominal speed. So if you have ODiff times nominal speed, which is change in speed for a second of acceleration, times nominal speed squared. It's interesting. Yeah, I need to learn more about speed squared here. It comes up a lot, but I know it's really part of, it's part of the magic. Anyway, see, I'm probably going to call it quits in about 15 minutes, just because So I've gotten into the weeds with this one little section because it is kind of one of the more interesting parts of the code. But not like down here, what are we doing? We're doing the overall, we're loading the block data. So this is preparing the block data for the shaping. For the shaping and calculating various things ahead of time. And we can continue to dig, but you have your T1, T2, T3, various things. You got total length minus this thing, which is your start feed rate, times your number of data points, times the time step resolution, which is again, so in other words, time. Okay. Yeah. Okay. Right. So yeah, T1 is time, and then that becomes time. So that is time times, again, 1,000 times the amount of hertz. Is number of data points. Okay. So we have this being, calculate the feed rate at the end of the acceleration phase. Oh yeah, is that true? Let's see if what it says this is. Calculate the acceleration and deceleration rates. Calculate the distance traveled during the acceleration phase. Think it's right? Well, T2P actually is coasting phase. I'm thinking this is acceleration plus this. 2.0 f times total length. Of course, that's an addition. Total length plus total length. How that should be done. Fascinating. So is it really? We take twice the total length minus that initial rate, starting feed rate, times acceleration minus end times deceleration. Okay, so I assume that these multiply. When these are multiplied, that's giving you a distance. That's giving you a distance, or I should say double a distance. And T1P at some point has got something that's doubled here, I think. Maybe not. Divided by A, yeah, sure. If it's dividing by A, yeah, you can't quite trust Copilot. It may try, but it doesn't always get things quite right. So maybe I'll do this. I'll Just see if it can describe what each of these things is. See how good it is at that. Yes, the total distance to travel. F of s is the starting feed rate. True, right? T1p is time spent accelerating. It is indeed. T2p, time spent coasting. Yep. Yep. How clever. So what does that tell us? Well, if we multiply T1, acceleration, twice the coasting, and T3, which is your deceleration, this should be a bunch of time. But it's interesting that the coasting time is doubled. I don't remember quite why. It's also multiplying, it's also doing twice the total length. Subtracting these lengths, which I guess are probably doubled again. But initial feed rate times this time tells you how much. I'm surprised it would be distance, right? Oops. Yes, in millimeters. In millimeters per second. In second. In seconds. And in seconds. At least I don't have to type, right? That's one of the nice things about this. Let's see if this gives us some clue. If I say Fs times T1p is the distance traveled during the acceleration phase. Why does it add the total length into that whole thing again, is what I wonder. Oh, I see. It's kind of like total length plus total length minus, in a way, right? They can kind of do that. You feel more inclined using addition. You know, up to a certain point, addition is just better, right? Doing a loop of additions is better than multiplication. On the other hand, sometimes multiplying by 2 can be, I suppose, probably one of the faster things, again, that these things can do. Nevertheless, when possible, I'm going to check again, make sure the compiler is optimizing it to addition, because darn it, it should. So anyway, that's fascinating. Then you get your acceleration, deceleration rates, I guess. Starting, that's the final feed rate, and the end feed rate P is your, yeah, the end of the acceleration phase, huh? So it could be the nominal rate, but most likely not. If you can get to top speed, great. And then max intervals. So interesting, it's actually called intervals. That's important to know. Finally, let's see. The end position, so X is moving, Y is moving, Z is moving, E is moving. and they're all being tracked in time through this. So each time it calls this, it's basically handling a single block. It's telling us, and it's preparing information that will be then used. You could almost look at this as like an expanded block. Like some of this stuff could be moved into the block, really. Although you don't necessarily need multiple copies. You're only doing one block at a time, right? So if this were all pre-calculated, stuck in the blocks, and then sent on, it may be that it's less dynamic. So interesting question. We can mess with that kind of stuff. But yeah, the stepper buff items and stuff gives us this udiff thing. Right. Keeping it unsigned is very important, I guess, because it optimizes it. But again, how many? Is this count ever going to go over, 16,535? I don't know. So it may be that this could be signed, and then I wouldn't have to do any of this crap. But it does seem that it's meant to be circular, so. Or yeah, it's counting up the number of items based on, again, produce index, this should just be head and tail. Or, head should be consume and tail should be produce, I think. I don't know what we call it now. But yeah, I'm going to see about that. At the moment, I do have the Y and Z turned off, so I like that it's noticing that. That's cool. Good editor, good editor. Yep, so we're going to call this Excel. And yeah, we'll put the decel in there as well. Yeah, it'll be cool when I can start to use the old camera again like I had intended to. Oops. Where is it? Oh, there it is. Yeah. When the screen's on, it's much better. But yeah, we'll get back to the old Ender 5 S1 soon. And I really want to play with the input shaping on this old machine. Big old beast, which is not a Core XY, and has a heavy Y carriage and a slightly less heavy X carriage, but definitely presents a challenge for input shaping. A little bit of a crowd today. It was nice to see Lou stop by. Hoping to get that belt printer down to Fort Worth and print up some things. But I may do some printing on it before then, and that'll be interesting to do input shaping on as well. That is a Core XY, but I bet it can benefit from input shaping as well. But yeah, overall, stuff's coming out really, really neat here. So I'm understanding the general gist. It's a lot of good calculations, figuring out, how long can we accelerate, how long can we decelerate, and then of course this is all really standard. And in fact, what I've just been going over is pretty much the same kind of stuff we have in our trapezoid generator already. The difference here is that it's providing some units that'll be useful for the input shaper, which comes below, where it starts to generate the points of the trajectory in the make vector bit, where it's, filling up arrays full of vectors and then running those arrays. This is where it gets really costly, is because we're filling up these arrays and then running them. And it's like, there's gotta be a better way. I'm thinking, this. I keep going back to this Bresenham concept, but I really think that there's something there. As long as we can, the problem comes, I think, in a situation where the stepper ISR goes over what you expect, and then you can't necessarily count on it being regular time. Yeah. So, data points of the trajectory, yeah. So it's pretty much what ours is doing, except the Marlin one is running. It's very interestingly, what it's basically doing is taking for each step that it receives. First thing it does is it chops the number of steps in half. So, there are a couple multiplies and divides by 2 in here that I can see would be sort of um, uh, analogous to what we've done in our own input, in our ZV input shaper. So once you have half the steps, then you've got to we're going to generate a step here, and then we're going to generate a step at, this other point in time. So naturally, we want to cut them in half, and then we'll just take for every step we generate, we'll generate a corresponding step at the future interval, assuming, that future interval is reasonable. You might be doing some kind of really slow move where it's like each step comes a 40th of a second apart or something. I can't imagine that would be that slow, but you could be moving that slow. And then you'd have this weird, race kind of thing going on with the, so we have to make sure that, the steps are far enough, or close enough together, I should say, then that we can actually stagger them. And also the staggering is interesting because, you can imagine a situation where you're like, well, I want to do this future step at this time, but there's actually a regular step scheduled for that time. It's like, well, as long as there's a regular step scheduled for that time, maybe we don't need our step. That step is going to take care of the cancellation at that time. But we do need to have, you need to have all the steps. So it has to basically come in somewhere. So you either stick it in a little before or a little after. Yeah, it gets a little weird, but it's overall working. I think that's where the other shapers come in, the advanced shapers with the extra parameters. They kind of can take care of some of those overlaps. Essentially, I think that's part of what goes on there. Is there's these overlaps, and it's got to deal with them. Oh, that's interesting. E raw Z1, E advanced Z1. Hey, you know what I could do is here. Good old C++/C. We'll set them both to 0 all at once. Do the same here. I just feel better doing that. Yeah, I guess I won't do it there. There I will, though. Sure, why not? One over length. We'll see where that's being used. Of course, we're multiplying. And 1 over length, what's that about? We want to be able to divide by something. So yeah, we don't have to necessarily give a name to that unit. It's just a reciprocal of the length. All right, cool. Well, that's interesting. Millimeters per second times millimeters per second times 1 over 2a. Apparently that's millimeter units, it says. Really? Do I trust that? I wonder where that comment comes from. I wonder if that's like a little bit of wisdom that Copilot has. Oh, sorry, CodeCam. Thank you. We're back in CodeCam land. Yeah, sorry about that. Yeah, at the moment I was just doing a little cleanup, which is basically, you really need to know, I was just doing this kind of thing, joining up lines that are basically the same units, all related, just setting them in one line. So yeah, that kind of thing. Clearly it's getting a little late. And then I was going to do this bit where I just kind of get that and call that what it is. And it's just a 1 over length thing. Don't have to give it a unit, but yeah. The total length and then 1 over length reciprocal of the distance. Direction, of course, is the current direction bits. And also this, I think we may have more axes, and therefore direction bits is probably going to be getting a unit of its own later, if it's not already. Oh, it is called axis bits type. So actually we need to do axis bits t for direction. Even though it might be really large at some point if you have like 9 axes or whatever. As long as you have fewer than 8, you're good. 8 or fewer. Direction. Cool. Yeah, time for a beer. What time? 9-ish? Yeah, I've actually been not having beer because, you know, Canada says that no amount of alcohol is good for you. 9 out of 10 doctors say no amount of alcohol is good for you, but I don't know. I'm feeling in the mood. Also, it is 9 o'clock. You know what that means? Anyone? That's right. It's time for the next episode of The Last of Us. So I got to go check that out. I've been looking for that. I've been very excited for that one. So that's interesting that we did not use divided by d there. Or if I did, it was negative or something. Goodbye, grapher. Nope. I'll come back and I'll try graphing at some point. I need to definitely get out my numpy and play around with these numbers and just watch them go. I actually did write at one point just like a separate piece of code to run motion and just watch it. And of course you can do that separate from Marlin and graph it out all day. So I may do that at some point too. Well, I thought it would be a little neater if I did that. And yeah, 0u. All right, we're making some sense, I think. Oh no, one of the actresses from Last of Us died? Annie Wersching? Was that the old lady from episode 1? She was definitely on in years, but what an actress, man. I mean, I assume she did her own running and screaming stuff there. But maybe they had a stunt person, maybe they had Alex Gray, come in and, or not Alex Gray, Joel Gray. Yeah, Alex Gray, man, he can do whatever too. But yeah, maybe Joel Gray did a little. I mean, he's done Yellowface before, so why not, Elderface? Of course, I'm referring to Remo Williams. The adventure begins. All right, so what the heck? Well, I'm making some sense, which is good. So we looked through some of the new motion code, which is applicable for a very simple Cartesian situation. And I can see ways to expand it for more axes, so that's really cool. And that means, of course, it means lots more arrays of stuff. Another possibility is, well, when you have a core XY is one of the things that we have to tackle kind of at a slightly earlier point. Oh, she played Tess for the game. Okay, yeah, she wasn't in the show, and I was wondering why, because they brought in a lot of other people from the game to do parts. Some of the voice actors doing the same part or another part. Like the leader of the Fireflies was same actress. The guy on the radio in episode 1, the smart one, not the other one. God bless him. The guy on the radio, he was actually the voice in the game of his brother. What's his name? But Joel's brother. So yeah, that'd just be pretty cool to see who else shows up. But yeah, sad to hear that one of the players died, because we need our artists, man, to remain immortal. Immortality today. Let's get it fixed. Let's get it working. We can extend some lifespans. Just of our favorite actors, Paul Rudd the shot that he needs to live forever, right? I think he already had it, but we're not sure. Let's start that Paul Rudd creatine rumor. Let's see. Oops. Some of these things do need to be wrapped just for safety. Just in case. Yeah, the cleanup never quite ends. It's true. Whoa! Okay, I feel like I know what I'm doing now. I'm getting into it. Yeah, so in our next session, whenever that is, probably in the next couple days, I'm going to go a little further with this, and we'll look at continuing the final cleanup optimization and putting it all together, and building it and putting it onto something. Actually, still with the Ender 5S1, actually I have a whole bunch of work to do on its fork, on their version, which is based on 2.0.8.2. I could bring it up to speed. Maybe I could bring it up to date with 2.11, which is where this is, and then try this input shaper on there. But I really wanted to get it to 2.1.2 and use our ZV input shaper first, and just give it a run, tune it up, see if I can use the accelerometer on my phone to do the tuning and stuff like that, because there were some good suggestions there, and get some nice accurate readings. And then if you can use your cell phone, that'll be cool. Motion shaping today, immortality tomorrow. Tell me about it. So anyway, yeah, Don't forget to check all the links for all the things, and I'll be back soon. Real soon. Love y'all. Bye-bye.